Before we get into the video, an organizational note. Apparently YouTube doesn't allow videos that are longer than 12 hours. And this video was initially over 24 hours. So I split it into 3 parts. This is the first one. Enjoy. Welcome. The next step for Plum, I believe, is thinking more about function resolution. So basically when you call a function, we somehow need to decide which function to actually call. And I have some thoughts about that. And I want this to work unlike in Martinez, which is the current default. So let me maybe show how that works. This is the compiler. I'm just going to create an example Martinez file. And let's maybe close that up and write a main function and just get that to work. I want to run compiler playground. Oh yeah, kind of that needs to import the standard lib, which is somewhere here, maybe. Yeah. So you can see that this works. Function resolution in Martinez. The interesting thing is, first of all, Martinez has function overloading. So you can define functions with multiple functions with the same name that accept different arguments. So you can, for example, write a foo function that takes a value and, I don't know, just returns that same value, and another foo function that takes a string and returns the length of that string. And then in here you can say foo of 5 and foo of high, and print both of these. Oops. And we see that it prints 5 for the 5 and 2 for the string, because that's the length of the string. So that's already pretty cool. And because, obviously, because Martinez has uniform calling syntax, you can also put the first argument to a function on the left side and put a dot in between there, leading to some sort of like method chaining, method feeling like stuff. Okay. Now, the weird thing, or I'm just gonna show that. You can write generic functions. For example, let's say we have some function bar that accepts some t that is generic over type t. So you can plug any t in there that you want. And bar can call the foo function. So you can do value.foo. And let's say this returns an int, for example. And then we could also call bar here, and that has the same result. And that may be surprising to you, because this bar function here, it looks kind of, how does this bar function know which foo to call here? There are 2 matching ones. And how this works is the same way that C++ templates work. So this generic code is actually not type checked. Instead, each time you use a function, that function is specialized and compiled for concrete types. So the compiler doesn't even look at the bar function, and for that matter at the foo function, until it sees this call. And then it's like, oh, okay, you call some sort of bar function with an integer. So I'm going to compile bar for t equals int. And then it type checks this function and it says, okay, so value is an int, and here we call a foo function that accepts an int. Okay, so it must be this function. The compiler specializes this code for every type that this is used with. For a language like Martinez, that enables some really cool patterns, and I think that's for Martinez, that's the right, that was the right decision. That is a really nice sweet spot in this language design spectrum, where if you have a small language that is intended to solve, more like small problems, then this is really concise this way, because what this allows you to do is to write some sort of generic function, and without specifying some sort of requirement of t needs to support a foo function. Without doing that, you can just immediately use that and plug any value in there. In fact, the standard library uses that heavily. So let me maybe show the standard library hash map. Yeah, it's here. It's a map. I'm not going to go into detail of how this works internally, but the point is that, for example, putting something into a map. Into a map from some key type to some value type. It hashes that key. That means that this key, there has to exist a hash function for this key. Only then will this code compile. Meaning if I don't know, create a map that maps 5 to high, this will work. Well, okay, yeah. Now the main function returns map. That's not what it claims it returns. Yeah, but this compiles. But if I put something weird in here, like I don't even know, flops, and flops is defined as a struct that is defined in here, and obviously there is no hash function for flops. We define a new type here, we create an instance of that, and this flops instance, putting that into the map should fail. And indeed it does. Because now it says, I try to compile the main function, I try to compile the map constructor function thingy with one single map entry from flops to string. That's the arrow operator actually is just a function that creates a map entry. And then it internally tries to put that map entry into the map. So yeah, here we see that raw insert that we saw before that tries to call the hash function on flops, and it doesn't work. Oh yeah, the hash function is actually defined globally, apparently. So there is a hash function in the standard library that is generic over AT that can hash any type. What it does is it creates a hasher, and then it calls hasher.hash. So for our flops, there needs to be a function with this signature, a hash function that accepts a reference to a hasher, this one, and a flops. And that doesn't exist. And for small code projects, for this is what Martinez was initially intended for, like advent of code puzzles, like projects that fit in a single file, basically. Even the compiler is written in a single file, so I really, this was basically the scope I was thinking about. I have this project, it's like a single file, you put everything in there. These kind of toy projects, these simple projects. This is a really powerful way of coding, I think. Because for your advent of code solution, you don't want to define interfaces and implement several interfaces or traits or type classes or whatever for your types. You just want to write a hash function that accepts something, and now you can put that thing into a hash map. That is simple. Of course, it has the trade-off that errors are no longer local. What do I mean by that? Rather than being told, hey, this map function, you try to pass a flops in there, but it doesn't support hashing. Well, we get something quite similar. I need, the code needs some sort of hash function for flops. So I think the communication here is actually fine. But it also tells you this kind of internal stuff, which is okay, I would say. The big drawback is that now we can't check code in isolation, especially generic functions. So this function right here, if there is something, some garbage in here, I'm actually not sure if this will compile. If we don't use that function up here, so we don't use a bar function, well, yeah, the main function is supposed to return nothing, so this map I'm going to ignore. Ignore is also just a function from the standard library that takes an argument and has an empty body. Same error with this one. Let's just comment out everything. Let's just say we have a main function that returns nothing, and this code compiles, even though there is nonsense in this function. And that that is fine for small scoped projects, but this can really bite you in the ass. Because, you might think your code works, but actually some part of the code isn't used, or it's only used for specific types where it just happens to work. For example, in our compiler, we have all these different compiler stages. For example, the pesto, they have some structs, some enums, and so on. And here they have a write function that is generic over a writer. The way the write function works is that in the standard library, there is some sort of IO thing. Yeah, and here's the print line function that can print any value by calling the print function and then printing a new line. And the print function calls standardout.write. Standardout being this print thing, and write being a generic method that should exist for this value. So you can't print anything where there exists a write function for that. And internally, the write function then uses this write byte or write bytes function to actually put something into the print, which then performs a syscall. Yeah, it's more like a way for the bytecode VM to trigger something in the parent host process. Anyways, not going into too much detail here. The point being that in order to support printing something, you just have to create these write functions for the type. But they are not tested. And what happened a few times by now is that I changed this pesto representation, and I added maybe some operations here, or I changed how some of these things worked. And because in the main compiler file, printing these intermediate stages is commented out, that wasn't an error. The code just compiled. And it wasn't even notified that now I'm missing a case in this switch maybe, or on this switch. So there is definitely a trade-off between having these sort of generic duck typed, having these C++ template like duck typing generics where you don't check the code until it's used. So what I want to do one additional drawback of this is that this only works because the printline function from the standard library, it can call this write function, and that gets resolved to this write function over here. So it only works because all functions share this one giant uniform namespace. As soon as you have to import functions, this can't import the write function for our specific project. That is nonsense. So this approach definitely has its drawbacks, because these dependencies between functions, they are implicit and they kind of rely on function names and functions being globally available. So for Plum, I want to do something different. I want to basically be able to check every function in isolation. So this code right here would not compile, both because this is not defined, but also because you can't just call foo on any t. This code would work if there is like a function foo that accepts t, like any type, and this function is in scope here. Then it would just call this function. So I want to check generic functions in isolation. That leads to the question, how do you define behavior? Like, we have this function, it's generic over type, but it also needs certain behavior for the type. For example, our map function, it requires that the type supports hashing. Some sorting function might require the type to support comparing the type to itself, you know. And many languages go with kind of these static interface-like things. So in Rust, for example, the way you would do that is you say, I have this key type, but it needs to support some sort of hash trait. And these traits, or like these kind of things on the right here, they are a new language construct that basically tells you which functions are available on that type. So then we can type check this code in isolation, because we know that the key is of type k, and k implements the hash trait. We know that there exists a hash function for k. And that means even though we don't know the specific key type here, we don't know whether this will be an int or a string or something, we just know it's going to be something that implements hash. That is enough for us to prove that there exists a hash function that we can use. Yeah. Of course, that also means that you need some way to implement these traits. And languages take different stances on this. Some languages do that implicitly. So as soon as you write a hash function that accepts an int, for example, now you can pass, now you can basically use the map where int is a key. In other languages, like Rust, for example, you have to explicitly say, I implement this hash trait for int, and then you have to put your functions in there. And these groups of functionality, this group of behavior, is called differently in many languages. I've seen the name like interface in Java, for example, and in many other languages as well. In Rust, it's called trait. In Haskell, it's called type class. In Rock, it's called ability. So yeah, the concept is basically the same. We want to attach some sort of behavior on something and specify how something can be used. So that then in generic code, we can require certain behavior to be supported for some of the types. And I believe this works in principle, but there is like a fundamental, I think this approach is not super nice for Plum. It doesn't quite work with the way I like to code. I'm going to explain why. Because traits, they suppose that there exists one canonical way of doing something. And especially for a structurally typed language like Plum, here we just, you don't even have these kind of named types like point or something, but instead types are basically just aliases to structs, like this. So writing a function that accepts a point is similar to, is exactly the same as writing a function that accepts this sort of struct. Yeah, the syntax is all messed up. It's in Plum, it looks cleaner. But my point is that trying to attach behavior to types is something I wanted to get rid of with this kind of data-driven functional language design. In traditional object-oriented languages, every object is specified using its behavior, using its functions, its methods, how they are called. And you have to basically talk with that object to inspect that, to get information about what's inside. And that is nice because it allows you to kind of create these objects that are compatible with existing code. But it also complicates things because you don't really know what kind of object you get. And I guess the extreme example for that would be Smalltalk, where even something like a 2, like a number, addition is just a function that you call on this 2, and it's going to return you a new number. That means that every code that every function that expects some integer, you can also call that with, Smalltalk is dynamically typed, by the way, you can also call that with some custom object that also understands the plus function. So your code automatically works for complex numbers, for example. That has some drawbacks, of course, because now you can't even inspect the state of these objects. And that's the entire point of object orientation. That rather than inspecting something directly and having this transparent view of something, you treat these objects like actual things that are alive, that you have to talk with to get information out of them. And that's nice because you have this clean interface, but it also means that you have no idea what's going on inside of that object. In some cases that kind of complicates things a lot. Because the way I look at things, objects, like data should not be alive, I believe. You shouldn't just be like, I have this thingy that you can talk to, and that works, yeah, but that shouldn't be the basis for most programs, I think. It is way easier if data is this kind of a dead thing that just exists, and you can deeply inspect it. You can look at the, I don't know, bytes or the actual stored stuff in there. And then there are these kind of higher level helper functions, maybe, like you have some map that has this, there's just some state, basically. And then you have these helper functions which allow you to semantically operate on that data. That was like a very abstract explanation. Sorry about that. My point being that in general, I believe that separating functions and data, like separating the data and the functions that operate on them, gives you new opportunities, because now you're not, at the point where you define your data, you are no longer thinking about how is this data going to be used. You don't have to think about that. But instead, you just define some deeply inspectable, transparent data, and how that is going to be used depends on the use case, and that is extendable. That means that rather than trying to extend over data structures, like in object-oriented programming, where your code automatically works for new data structures, you try to make your code extensible over the behavior. You have your usual data structures, but you can kind of attach new behavior to them. I believe that's a way more intuitive way to think about coding, especially if you're coming from a sort of mathematical background. So, what's the problem with attaching behavior to types, like you see in object-oriented programming, but also in traits in Rust, for example, or in typeclasses in Haskell? The one drawback of that I see is that you have this one canonical way of dealing with some data. For example, for the hash function, there needs to be this one canonical way of hashing a value. And turns out that there isn't really. Like even in Rust, if you have a hash map and the keys are some big objects, maybe you want to hash the object by like deeply traversing that and generating like a really high quality hash of that is really unique for that value. But maybe you also just want to, maybe the performance of the hashing function is your bottleneck and you want to optimize that. So you just want to kind of inspect the top part of the object without like deeply traversing into all of that. Which means there may be like two competing hashing functions, like two ways of hashing the same type. And it's not just hashing, even like this extends to basically everything. Even, for example, addition. If you add two numbers, you're like, okay, there was one obvious way to add these numbers, just add them. But the question is, what if these numbers are really big? And especially, numbers are like 64-bit integers. What if that overflows? What do you want to happen? There are cases where you want that to kind of panic or crash, or throw an exception, where you want that to fail. But there are other cases where you just want to get the lowest to kind of wrap around and get like a really small negative number. And depending on the use case, you want one or the other. In Zig, that is kind of solved, I guess. So in Zig, there are two operators for that, actually. There's the plus operator and there's the +% operator, which wraps around. Most arithmetic operations have a wrapping operator as a separate thing. It becomes even weirder for floating point numbers, because in the hardware, there actually exist different circuits for doing like a high quality multiplication that is really precise, or doing one that is fast, but not as precise. But depending on the use case, these performance benefits may be worth it. If you're doing some machine learning stuff where you have giant matrices that you want to multiply, you'll want to use the faster one that is not as precise. So yeah, having this one way of doing something, this one canonical plus function, this one canonical multiply function, this one canonical hash function, that might work if you are like new to the problem domain and you're like naive and you see, well, this is the way things should be done. But in actuality, things are often way more complicated, even for fundamental stuff. And that's kind of mirrored in mathematics. Let me maybe pull up some mathematical definitions. Because if we go back to math stuff, I think there were these calls like able group, how is it called? Like ring, mathematical ring, I don't know. Yeah, in math, instead of types, you operate on sets. For example, there's a set of natural numbers or something like that. And the way you usually associate operations with these sets is explicitly. So here, for example, we see that for some sets, in our case, there would be some types. There is a way of adding these types and multiplying these types. And they also have these extra, extra stuff. I wanted to see. That there was some way where that, at least in some literature, these concepts like rings, mathematical rings, or abelian group. That's the one I was thinking of. These this is a simple mathematical concept, where mathematicians kind of stumbled upon a very similar problem, which is we have some sort of type, for example, natural numbers, and we want to associate operations with those types. And what they did is, for example, an abelian group is a set. In our case, that would be a type and an operation. And you can use that operation on elements of that set. In our case, you can use maybe a multiply function, like a star function, on values of the type A. And in mathematics, there are the operation has to support specific properties. And what they do is, rather than saying the A has to, like the set A has to kind of intrinsically support this operation, elements of this thing, what they do is they talk about this as explicit associations. So to qualify as an abelian group, the set and operation, this right here, must satisfy these requirements. Okay, so basically they have this is the abelian group. This right here, the abelian group is a tuple with the set and the operation. So rather than you just have this tuple that associates a type with the operations that work on them. And this is interesting because this multiply thing is not an inherent property of the elements here, but instead there may be multiple ways to define, there may be multiple abelian groups on the same set. They are just different tuples that have the same A but different operations here. And I believe that should be the way that programming languages work as well. So if you have some generic function, okay, I'm actually not sure how I want programming languages to work, but this is kind of an experiment that I think has a solid mathematical foundation and makes sense conceptually, and that is to, instead of attaching functions to types, you instead build up these explicit tuples, these explicit groups of operations, and pass them around. Yeah, so let me maybe show how that might look like. Let's say we have some sort of type. Like, let's maybe look at the list module from the Martini standard library. Here we can see, it's like the mem module, what I'm thinking of. Here, we have some sort of, we have a sort function for sorting a slice. And what it does is it compares two elements of the slice. So these elements, they have to support the comparison operator. Rather than doing it like this, I think a cleaner way and more extensible way would be to define some sort of sort function. Yeah, let's maybe take this signature as the starting point. That is generic over some t, and it takes a slice, and then a compare function that takes a t and another t, and it returns an ordering or something. And usually in languages like Rust, for example, there are actually two functions. There is a sort function, and there's a sort by function, which accepts this extra thingy, this extra function for comparing values. And there is a sort function that uses some sort of ordering or odd trait on the type, and uses the behavior that is attached to the type. And to me, that kind of is emblematic of the underlying problem. Like, there is often there is no one way of doing something, and having this arbitrary border in your code between these are operations that are intrinsic on these types, and these are operations that are kind of more freeform that you have to pass around. This disconnect, having this hard gap in between them, like separate language features for both of these, that kind of goes against what how things should be, I believe. So I think rather than going the Rust approach, where you say I have this sort function that a t supports ordering, and then I can sort the slice. This would kind of be how the function signature looks in Rust. Rather than that, I think you should only use these kind of functions, where if you want, you can write generic functions, okay, functions that are generic over some type. But if you want to do operations on that type, you should just pass functions around. That is simple, that is extensible. You don't lock yourself into this one way of doing things. You don't have to introduce a completely new language construct like interfaces or traits. You don't need to associate these kind of intrinsic properties to those traits. Like, that's the fundamental problem that I think mathematicians realized. These operations are nothing intrinsic to types or to sets. Operations are always a separate view on these. Yeah. So, that being said, at some points, passing around a bunch of functions as separate arguments may be kind of bothersome. So I think that's for Plum, we might want to at some point you find something like this, like an orderable, like order. And let's say we have some sort of ordering an ordering implementation for some t. We could define a type alias for that. That is just a function that accepts a t and another t, lowercase because these are type variables, and returns an ordering, which is an enum defined in the standard library. And then things that that are generic over some type. Let me write that in Plum syntax. So this would maybe take some sort of slice, which is a slice of t, and it needs an ordering, which is an ordering impl of t. I think you should write your code like this. And yeah, if this is just a type alias for one single function, that may be kind of, why you have this type def. But I think for multiple functions, that kind of really, that composes really well. Let's say we have some implementation of a map. We could say, to create some sort of map from a key k and a value v. Like from some entry, maybe there's a map entry of key and some key and value. Then we also need to accept some sort of ordering, some sort of like map hashing and equality. Like in this case, what I'm trying to get across, the key type has to support two operations: hashing and ordering, like hashing and equality checking. And these two operations, they need to be somewhat related. They need to fulfill some properties. For example, if two values are equal according to the equal operator, the equal function, then the hashes should also be equal. So I think the way this should work is just have some sort of hash impl of the key, except that as a separate parameter. Boom, like that. Let's write maybe, let's say we have some sort of list or slice, and we want to convert that slice to a map by putting all of the values of this into a map. To do that, I think you should also have to provide an implementation for hashing the key type, and hash impl being implemented as just a struct that accepts that has a hash function that takes hash impl of some type t, that takes a t and returns, I don't know, an int or something, and it has a compare function that takes a t and another t and returns an order, and returns just an is equal function is enough, like this. And you can see that this can be extended to other stuff as well, like have arbitrary functions in here, and you still only have to provide like a single parameter here. And I believe this kind of coding pattern is somewhat cleaner, because now you can decide what kind of hash function you want. If you want some very shallow, low quality hash function, but that is really fast, you can do that. If you want some deeper, more sophisticated hash function, you can also do that. So you're free in parameterizing this behavior of types. Yeah. And of course, for like the usual standard library types, like integers, you would just have a global constant or something, like int hash impl, this would kind of be analogous to the impl block in Rust, where you just say, you know, we have this hash thing that takes an integer, and what it does is something like this, yeah. It hashes that integer. And this is defined in the int module. And yeah, let me get this right. Yeah, something like this. Yeah, and this would be defined in the int module, which means that the hash function that takes an int is in scope here, and the equality operator for ints is in scope here. So you can kind of bundle up these type-specific behavior, but rather than having this separate type level thing where those kind of get implicitly attached to types and passed around, you just create values and you explicitly pass them around to functions. So if you have some slice of ints, you can then just do, you know, to map using the int hash input. And of course, because that's a common operation, we would also, you know, create this kind of function to map, where the slice is a slice of map entry int and value, and that just calls this other function. Like this. So you can in the end, you know, you can just do, you have some slice of integers and then you just call toMap on that. Like this, in the end, how you use that stuff is the same. It's just that there has to be some sort of path, some sort of explicit, you know, explicitly saying, well, by the way, for integers that should use the int hash impl that is defined up here, and you know, stuff like that. Right. So I think that's basically what I wanted to talk about for today. I just wanted to get across this kind of design idea and explain why I want this to work that way, you know. Yeah, maybe summarize the key points. I don't think traits, interfaces, type classes, they're the right approach. I think in general, attaching behavior to data, like you do in object-oriented programming, is kind of, it creates this weird dependency, because oftentimes behavior is not intrinsic to data, or on that note to types, you know, but instead there are different ways to look at the data that should be independent of the data itself. So there should not be one canonical way to deal with some data. That's why I believe that, and that's why I like having top-level overloaded functions instead of having methods defined on data. That's why I like this mathematical way of looking at things, where defining a new property like an abelian group or a ring or a hash thingy is not something that just exists and that's an intrinsic property of types or of sets, but instead that's an explicit grouping of operations. And yeah, I believe this is an approach that doesn't have this, that doesn't create this artificial duality between operations that are inherent to types and other operations that are not inherent to them, but instead it treats all operations as being something that you can customize. And it encourages starting with a concrete implementation, starting with just, you know, a hash map or that has integers as the key, maybe. Starting with, you know, start with concrete functions that work on concrete things, and then later on, when you need more generic versions, which, to be honest, you don't need for many functions, you know, for hash maps, sure, I see that, but like most of the time for your actual application logic, I think the right approach is not to go the Haskell way and be like, let's write the most generic function possible, but instead start with generic types and then kind of generalizing over that, making things more abstract adds complexity, that adds indirection. And that should be represented in the language. That should be represented by passing around this behavior, this extra behavior that your code is now dependent on. This dependency needs to be explicit in the source code. That only makes sense. Yeah. Okay. Yeah. One additional kind of open question that I haven't looked at is what will this allow us, and how does that interact with comp time stuff? Because what that allows us to do is to look at functions in isolation. We don't have functions like this where we kind of depend on the behavior being available, but instead that behavior would be passed around as explicit functions or structs of functions instead. And so yeah, you can check every function in isolation. That's the goal. Of course, this kind of falls short for some some functions that are designed to work on comp time, on that comp time level on types. So at some point I probably want a function that passes some JSON to a type that we don't know yet. That's kind of inferred from the JSON string, which has to be comp time known. And it returns a type specific to that JSON string. That currently doesn't, like, at least for these kind of functions. I think we even have a function that works on, like, does some crazy type stuff. Yeah, for this kind of function, we don't really, okay, yeah, I'm not sure I can type check every function in isolation. Because as soon as types are first class things, we could check, is the type of this thing bool, for example. Then we want to do something. And yeah, I'm not sure how that's going to work out. Anyways, enough rambling, because I have no idea what, like, I haven't really thought about that yet. Okay. Yeah, my point being, I have some sort of idea what I want to do next. And yeah, see you then. Alright, so I guess the first step would be to implement that. So let's first write some code that currently works, but that's actually not supposed to work. So for example, let's say there's a function foo that works on integers, and it returns an integer because it always just returns 1. And there's another function foo that works on strings, also returns an integer, returns 2. Now what you should not be able to do is define some function bar that takes any any value of any type t and then returns an int by calling foo of that value. This should not type check. Let's also call that function like bar of 5 and try to compile that. Currently this works, I believe. I am compiling the compiler and then compiling the actual thing, and it compiles and returns 1, which makes sense because this is an integer, so bar is compiled and then foo is compiled. Yeah, and the problem is basically that we start from, we do this compilation lazily for concrete types. And that is when we do the function resolution. So we look at the main function, we see, okay, let's try to compile this. This calls bar with an integer. So we look for a matching bar function. This function matches, it works on any t. So we compile this for t equals int, basically, for the concrete type int. And then we see this calls foo of int, and then we look for a foo function, and this one matches, so we call this. That is, yeah, this makes sense, but I don't want this to work. I want this to be an error, right, as you know, without even if you don't call the bar function, just by writing this function, this should be analyzed, and we should note that, hey, here you try to call foo on, you know, any t, but there doesn't exist a foo function that works with any t. So you shouldn't be able to use overloading based on the actual value of the generic type, but only on the, you know, kind of look at each function, including generic functions generic over some type. Look at each of these functions in isolation and figure out which functions they refer to. All right. Yeah. So let's try to fix that. I have a rough idea of where we need to adjust the compiler. And there are basically 3 relevant compiler stages. Let me maybe go to the main file. Yeah. These are the compiler stages. Oh, I think there are actually missing some, like the pudding and pesto. Well, I guess we start with source code. Yeah, so this is kind of the area where we want function resolution to happen. The toast is just a syntax tree. It's a representation of the entire program that you wrote, basically of the file content, but in a hierarchical sense where we have you know, language constructs like variables and switches and stuff like that resolved. Let me maybe show that. Yeah, this is the toast where we see you know there are some functions, and these functions, they contain expressions, and expressions can be calls, they can be name, which then contains the string. You know, in your code it says the string foo or something is called, or the string bar. So this is like a very, you know, syntax tree. It doesn't contain semantic information. Names are not resolved. If you define a variable called foo and then use that later on, here it's just, well, you have, you know, a variable definition where the left one is a name, foo, and then stuff, and then later on in your code it just says, well, there's, you know, a name named foo here. These are not in any way connected at this compiler stage yet. And I want to keep it that way, because the toast should just be the syntax of the program and also be used for formatting and so on. It should be able to handle incomplete code, handle code that is not valid. All the code you write should be able to be represented as a toast. And the next compiler stage after, let's first look at the yogurt, which is a compiler stage that contains functions. Yeah, just functions, compiled and specialized for concrete types. So here functions are not generic anymore. Instead, functions, you know, we kind of have specialized versions for generic functions. And we can maybe even look at that, hang on, by just debug printing the yogurt, I guess. We should be able to see what that looks like. Yeah. Okay, well, this is easy. The yogurt just contains the main function that contains some comp time values and then returns them. Because in the yogurt, compile time evaluation has already happened. And, well, functions are specialized, but that's not really making a difference here. Well, oh, maybe it would make a difference if I'm not passing 5, but the argument to the main function, because then bar cannot be compile time evaluated because we don't know the value of the int that we're passing. So now we should see specialized versions of these functions. Yeah, we see main that takes an int, and yeah, makes, you know, it uses cast from int to int, and then it calls bar, specialized for int, and this is the specialized bar function for ints, and this calls the foo function for ints. And yeah, the specialized bar function for ints is basically this one. And again, if we would call bar with two different values, we would get two functions in here named bar. One would be bar taking an int, another one would be bar taking a string. The generic function doesn't exist here anymore. And I think the toast and yogurt, these are like compiler stages that have a very clear purpose or a very clear design. You know, you can easily explain the toast in a sentence or something. You know, it's a tree that represents the syntax of the program. And you can also describe the yogurt. It's basically, it contains all the functions that need to run during the actual execution of the program, not during comp time, specialized for concrete types. In between these compiler stages, in between the toast and yogurt, is the egg. And that's a kind of weird compiler stage. Let's maybe also look at the egg. Because the egg is it's kind of ad hoc defined. It doesn't really have a clear, you know, the vision, the design of the egg is not as clear as those of the other functions, of the other stages. Yeah, and it looks a bit messy. So what the egg is, it is basically a representation of all functions. So this will include all functions of the standard library, including like built-in functions and so on. But in here, these like expressions are decomposed into these simpler expressions, and expressions don't really have types yet. Oh, hang on. Yeah, this is the yogurt. This is the egg, and expressions don't have types here. So you can see that this is an int 0, and that gets returned. And here we call some other functions. Here we have a switch, but these don't have any type annotations like these expressions down here. I just realized I may be blocking some of what I'm trying to show. Yeah, so the weird part is that in the egg, local variables, they have been resolved. You know, we see that this refers to the ID of this parameter here. So that works. But functions have not been resolved because we don't have any type information at this point. So whenever there's a call, we actually just have the name of the function being called and the arguments. And then we have this list of candidates of functions that are visible in the current scope. Because the egg, you know, we have a single egg for even if you use multiple modules. So for every call, we also note which functions are visible here, so that we can then choose among these functions a matching function. And that is weird. Like, this feels kind of clunky. It feels like a workaround. And again, the behavior of how function resolution works, I want to change that. I want to make it so that even for these kind of generic functions, we already know which function we're going to call without knowing which types will plug into our generic type. So I think already in the egg, we want to have functions resolved, which means we'll probably need to adjust the way that we are converting the toast to egg, and also the way that we are converting the egg to yogurt. Yeah. And first and foremost, we also want to probably have types in the egg, at least some sort of, you know, not specialized types, like having it for specialized functions, like, you know, specializing generic functions for concrete types. But we do want some notion of types and being able to look up types. All right, so let's get started. This is an egg expression, and an egg call is down here. And instead of some candidates, what we really want is just, I guess, the concrete function that's being called. The way that these functions are identified is currently with the module and a string, which is, yeah, it is kind of weird, but I may change that later on. I don't know. Works for now, but doesn't feel super clean. Alright, so calls, they should already know which function they call. That should not be, you know, part of a later compiler stage to figure out. And every expression should also have a type directly in here. As types, we use plum types, which is basically a common type definition used in the egg, the yogurt, and also the pudding, the compiler stage after. So this, they use the same concept of a type, which is, I believe, hang on, type, yeah, which is defined in here, where type is either like a primitive type, like int or something, or there's a struct of other types, or an enum, or a lambda. Yeah, and recursive types are also somehow represented in here. Okay, so I think we need something very similar to this on the level of expressions, not just on the level of functions. So every expression also has a type. Okay, I kind of like that. Yeah, you can construct expressions using this add thing. So you can say expression kind int of 5 add and then some source location to construct this egg expression from that. That won't work because we also need a type. Yeah. Ooh, I guess let's maybe have some sort of expression constructor that takes a kind and a type and a source and returns an expression with these things. Something like that, maybe. And yeah, this won't compile because, you know, the compiler stages, they are not adjusted to this. Yeah, so in toast to egg, this is perhaps the most relevant part here. We have some places where we do this add shenanigan. Yeah, when adding an expression kind parent, we of course want that parameter to have some sort of type. Yeah, so we need to know the type, and it should be passed to us in here, like this. Boom, calling our expression constructor. Yeah, for integers, yeah, we should create an expression using type.int and the source of the integer. For this down here, what we do is we have some sort of call, expression kind.call, yeah. Oh yeah, this shouldn't have candidates, instead it should basically look up a function, I guess. We do have the functionality for that in the next compiler stage, because that's where we did function lookup until now. So let's maybe move that into the previous stage. Oh, it's actually reasonably small. That is nice. Oh. Hang on. Yeah, the specialization of functions should still happen at some later point, I guess. I'm not entirely sure about that one. Yeah, okay, let's just copy the lookup function and then we'll see what we do. Okay, so here we have functions for creating some compiler doing stuff. Okay, sure. Sure. The interesting part would be not entirely sure how or what, like. Hang on. So we have variable scoping. Okay, that is like a separate, you know, a separate concept, I guess. We have imports and exports. Okay, fine. And then in here, let's maybe add some little section for looking up functions. Yeah. The thing is, we don't yet have an egg. We only have functions in scope. And that would be some sort of, this sort of set, I guess. Yeah, and now we look for a function with a given name and arguments. And that returns a result of a matching fun, which would be like this, basically. Yeah. I think I'm not entirely sure about that. I don't know. Yeah, let's maybe first look at the body of this and then see if or how things work out. So I know that functions have signatures, like in the Martinez code, like these kind of signatures. So I think this should really just return a list of the matching fun contains a function directly. That is kind of weird, isn't it? Well, I basically want a way to identify functions, I guess. To have some sort of unique function signature, function ID thing that I can then return here and reference here. I have to admit, like, this is kind of weird. Like when looking at the definitions that are in scope, we have a list of def in scope. Okay, but def in scope has a module and then a def in scope kind, which can be a type or a function. Okay, so this is a fun in scope, and then it is a custom toast fun that is okay, I guess. I think in the egg, every function should have a kind of unique signature, something that identifies this function. Yeah, I don't know how that's going to work yet, but I'm gonna figure that out. So name matches, these are really just yeah, how are like toast functions matched to compiled to egg functions? So we create an egg function where the parameters are this kind of thing. Oh, okay, so we just take the parameter type, convert that to egg. Okay, I see. Yeah, okay, I see. Like in general, when converting the toast to egg, what we do currently is we have this, basically this list of all functions, and we just go over all functions and then add them to this list. And then we just return that. That works, that worked as long as functions could basically be compiled independently and they didn't need to know about each other. You know, because calls in the egg, they would just say, well, I'm calling this other name, you know. But it kind of fails if we already need to kind of know which other functions exist, what types do they accept, stuff like that. Because I think the better strategy would be to first compile all function signatures, basically. You know, just check which functions exist, what are the types that they expect, stuff like that. And once you've done that, you can then compile the function bodies. And if you see some sort of function call in the body, you can then look into this existing map, this existing whatever of all functions, and you can kind of match which function signatures match this call. And we can't do that with how things are working right now. So I think the first step would be to, rather than having a list of egg funds and building it up over time, have some sort of map, I guess, of toasts. Kind of toast funds, maybe, which would be a map from the There does need to be a map, actually. I'm fine with using a list, but it needs to have basically the function signature in there. Yeah. So some sort of egg signature. And what is an egg signature? Well, first it has the signature, which is just a string that is unique in the entire program. And then it should also have the underlying toast fund, I guess, to kind of enable compiling that. And also have parameters, which will be some sort of slice of types, as well as the return type. Yes, this looks fine. Yeah, I like that. And then what we do is this is only used for, basically temporarily while we are compiling stuff. What we do is we basically do this, and instead of compiling the function bodies, we just add signatures to this part right here, to this list. So for each of the built-ins, we just push an egg signature, where the signature is, to be honest, I don't know, built-in, I don't know, and then the built-in, is it just like that? I'm not entirely sure how that's gonna look. Yeah, the params are the built-in params. Hang on, there was this create built-in fun, yeah. So it has a signature, built-in signature. Oh, that is nice. And the signature has a return type in params. That is pretty nice. Oh yeah, of course this is also a possibility. that we somehow need to represent up here. Hang on, up here. For each of the built-ins, we kind of get the signature, and then in here, the signature will be built-in module. Colon, I guess, built-in, it will have params, which will be signature.params. It will have a return type, which is signature return type, and it has an impl, I guess, or toast or something, yeah. And this would be a maybe, because it may just be a built-in. Oh, hang on. Yeah, let's maybe do this. Egg signature. I don't know. Yeah. Weird. I should change this later on. Also, like user written code, but they closed fun. So this could then be an egg signature impl. Okay, so we have this egg signature. The impl field is missing. That is indeed true, because this will be impl egg signature impl dot built-in of our built-in. Okay. And then for the actual types, I guess, or you know, oh, yeah, here we iterate over the modules. Let's see. We check which definitions are in scope. We shouldn't need that right now. Not yet, at least. Yeah, and then we convert that to egg. I think what we want is to yeah, before even this is basically like its own little compiler stage, you know, very similar, like basically just aggregating all toasts into basically a giant list, a giant map, whatever. Not too sure about that, to be honest. Let me take a small break. Okay, so I guess I'm gonna rename this, because this is not really, this is the signature. This entire thing is more like a toast fun that we still need to compile. So maybe toast fun to compile or something, I don't know. Yeah, but it does have the parameters and the return type, and then the actual toast fun. Okay. So what I want to do is, rather than going over the entire over all of the toasts and following imports and so on, and then doing that same thing again later on in here, I want to do that only once, and in this list of toast funs to compile, each of these will have enough information to compile that function, meaning that it also needs the definitions that are in scope. So how are those called? In scope or something? Yeah. Usually these are called in scope, and these are definitions that are in scope. Like this. And yeah, let's maybe revisit that definition, like def in scope. Okay. That has a is either a type that is in scope. Okay. Or there's a function that is in scope. I think that makes sense. Yeah. And the function in scope is either that or custom. Okay, yeah, something like that. Sure. So down here, what we want to do is we push the built-ins with this signature, and the signature I think will actually have the, well, yeah, I guess this is fine. Signature in scope is just an empty slice for the built-in functions, because they don't need to be compiled anyway. They just kind of get mapped into Yogurt functions directly. And then for every module we compile, well, let's maybe call toast.prepare or something. You know, prepare them for compilation. I don't know. Yeah, so let's have some sort of prepare function. That takes a single toast, it takes a module, it takes the definitions that are in scope, it takes a list of, like a mutable list of toast farm to compile. Yeah, that seems right. And every function gets pushed to that. That should be, oh yeah, this doesn't yet get compiled. Instead we do farms.push toast farm to compile. And this one doesn't need the a compiled version. It's just needs a signature, which will be something, you know, probably the module colon the name, maybe, I don't know. Yeah, farm.name. Oh, and also the parameters, I guess. Parameter types, and those should be unique. Like there shouldn't be two functions in the same module that accept the same types. That is narrow somehow. Still need to handle that. Actually, let's edit it to handle multiple with the same signature. Yeah. Okay, so every function just has a signature. It has params. It has a return type. Let's. Oh yeah, this actually looks amazing. So we have params, we have a return type, and we also have, yeah, the definitions that are in scope and an implementation. In scope, we already have that here, and then the implementation will just be a toast to compile simple code, I guess, of the underlying function. And this is just, let's comment that out. Yeah. Yeah, I think that's fine. Signature is egg params. I don't even know what to do about that. Where's that defined signature? Is defined on built-in, and it returns a built-in signature that has indeed egg params. Weird. Okay, sure. Why though? Why? Let's not do that. Let's just say this. These are plum types. I think that is a fair assessment. Just do that. Boom. No message, no value, no stuff. No, these are just plum types. Yeah, that seems much better. Yeah, and then this should work. Okay. Let's maybe compile that, see what fails. Oh, okay, so stuff. This call doesn't work. String and source. Oh, right, because the function name is a string and source. We need to extract only the string from that. And once we have all the functions, then we can actually compile them. So here we just do compiled, I guess, is a list of egg funs, and then for fun, in funs we compile that function to egg. Boom. And everything that the function needs for that, like the module that it's defined in, the definitions that are in scope, etc., these should all just be bundled up in this function object. Okay. Yeah, I'm just gonna comment that out for now, and we'll see if that works. Yeah, this compile step down here, we probably don't need that, but oh yeah, instead we'll do toast fun to compile. We need, to compile that. We don't need this one though, I believe. I'm not entirely sure. And neither do we need this, because this entire thing contains all necessary information. Basically we just return something. Hang on, we return everything. Rather than pushing something to a map, we just return that directly. Yeah, this can fail, which is expected. Hang on, especially this can fail, yeah. So this entire thing needs to be wrapped in an OK. Yeah, module doesn't really, well, it does exist, I hope, maybe, egg fun. Hang on, it has a module, it has a name. Yeah, okay, maybe module and name and so on is a better thing than just drawing a signature here. Maybe. Yeah, probably. Okay, so let's not do this, but instead just store the toast fun to compile. Yeah, we have the param types anyways, so we'll also have a module and a name. Oh man. Yeah, and this will just contain the module, which will be the built-in module, and will have a name, which will be the stringified version of the built-in, like that. Okay, okay. And then these, something very similar. Hang on, what is going on here? toast fun to compile this call. That doesn't make any sense. So in this prepare thing, we push a toast fun to compile, and this needs a module. It needs a name, which will be fun name string. Yeah, and params. Okay. Okay, nice. And this entire thing will be that, and this is that. Okay, yeah. The parameters should have already been compiled, so this is just toast.params and toast.return type. And let's maybe not call this toast, but actually fun, because I think that's way better. Yeah, okay. And then we have the impl, which will be an eggfun impl.code. Well, actually, we'll just switch on the fun impl. If that is a built-in, then it's just going to be eggfun impl built-in, destroying that built-in. If this is some code, then what we'll do is this. Yeah, okay. Not quite. Yeah, like that. Yeah, we create a compiler and compile the body and do stuff like that. The founder params has those have a name. And the code contains the actual toast fun. So I think that's what this fun refers to. Kind of confusing, but meh. Okay. Assign slice of egg param to stuff. Yeah, these should not be egg params, these should just be plum types. And then for every parameter in fun.params, what we do is we just push the type in there. Okay. In scope is not in scope. That is hilarious. Let's fix that. Yeah, push param was going on there. We have a body param. Oh yeah, that needs a type. That is true. Let's maybe zip those with the actual types, giving us the name and the type like this. Slightly convoluted, but sure. Oh yeah, the zip only works on iterators directly. Mutable iterators maybe? Nope. No, that seems to work. Okay, so line 455. What we do is we don't... Oh yeah, plum type.int is not a thing. Instead we use plum type.primitive int. Yeah, same with string. This would be an expression of the primitive plum type string Okay, here we have a struct. What is the type of struct that we create? Well, now toEgg returns an ID. So I think we need types, which will be a from string to plum type, yeah. And then we basically do this. We compile the field giving us an ID, and then we put that ID in there, and for types we put the field name. I mean, we can also do this. Yeah, and the type is, hang on, that would be body.get of that ID probably, giving us the expression and then getting the type of that. And then we can do something like this, maybe. Okay, so .get doesn't exist on an egg body compiler. Here's the egg body compiler. We can only, well, what can we do? We can push a parameter, we can push something, we cannot get something from that. That seems like it should be possible, so let's maybe do that as well. Get body will be an egg. Yeah, okay. That returns an egg expression. And the ID is gonna be the, hang on, we have the ID. So just do body dot parent dot expers dot get ID dot int, giving us an egg expression. Right? Yeah. And then in here we can say this should be an expression of the type. Well, yeah, plum type dot struct of these field types, and also the ampersand in there. Boom. Yeah, next enums. So I'm just realizing, like, we basically need to do the entire type solving, type stuff that we do in the yogurt, which is quite a lot actually. Like in here, yeah, look at the size of this compiler stage. Damn. Ooh. I'm not super happy how that's gonna work out. This is already moved over. Yeah, okay, this, like, compile time execution, we don't do that yet. Conf time cast. I'm not sure what to make of that. Yeah, we probably need some sort of casting and stuff like that. which, to be honest, kind of sucks. Not sure we need captured variables and stuff like that. Probably not. I think. But still. Yeah. Okay. This is fine, yeah. So we have candidates. Let's hang on, we have variable scoping, boom. Stuff for looking up functions, okay. Still need to fix that, but that is fine. This is the actual compilation. Well, not really actually, this is just the preparing stuff for compilation. Well, okay, I guess this is the actual compilation. Yeah, fine. Fine. Okay, so rather than prepare, let's maybe call this like collect functions or something like that. I don't know. All right. Cool. So here we are compiling something to the egg. We have strings. They should work. We have ints. They should work. Amazing. Just gotta go through that step by step and not get overwhelmed. That's basically the idea. Okay, for enums, what we do is, well, basically we need to body.push egg expression kind.enum. That's an egg enum. Yeah, that makes sense. Okay, but the type of that is also important, and that means that we need to kind of first compiling all the value, the payload, and then well, you know, compile the payload, then say, well, we actually want this with some expression. But what expression? Well, the plum type dot enum with a map that maps the name. So to the values type, and that would be body.getValue.type. Okay, yeah, that's the enum. The switch is going to be complicated because, yeah, if we want to resolve functions in the egg, we also need to worry about, you know, having a switch. In one case returns foo, the other one bar. Now let's look for a matching function. Like that entire joining of types and so on has to happen already in the egg, which will be fun. So switch.condition.toEgg. Yeah, that seems about right. Then we have cases. So we snapshot the variables that are visible. We say create a body, you know, a body for that case. If the case has some payload, then we also define that. Okay. And here we need the payload. Oh yeah, we need to get the enum payload type thingy. So let's get the condition type maybe. That would be body.getCondition.type. And then in here we would say the payload type is the condition type. We know that's an enum, yeah. And from that map of payload variants we get the payload, giving us a type. Yeah. Let's maybe break this onto multiple lines so that it makes sense. Yeah, this seems reasonable. Okay, yeah. And then the thing the branch returns something. Nice. Let's actually put like an egg body builder in here directly, so we don't yet finish the enum case. Oh, is it like egg body compiler or something? Yeah, okay, sure. Maybe a tuple of that, and the ID that should be returned but is not yet returned. And then we also have the types that those enum cases return. Case types. Yeah. We compile the body, we have the return thing that should be returned. And then in these cases we just put in the case.similar string. No, that doesn't, no, this doesn't seem right. No. There should be the case symbol in here, not the enum, not the binding for the payload variable. Okay. Alright, we have a common we have, let's maybe call this variant types or something, and directly unwrap that in here. Then we don't need to do that down here, and here we can just say variant types dot get boom. Yeah. Or like payload type, something like that. And that's just gonna be that. And then we can kind of merge that like this. Amazing. Cool. Very cool. Yeah. Then what we do is we have a switch with a condition with variant types. And here we have the case builders, case compilers, I don't know, something like that. And there we put the case body compiler. Amazing. But also the value that we want to return. So that now, after all those cases, after we've looked at all those cases, we can then join the types and insert cast expressions and finish these bodies. Yeah. That does mean that we also need to put type in there. You know what, let's maybe for each of these cases, let's maybe do like variant, like symbol, this case dot symbol dot string, and then in here we just do symbol. Yeah. So the case type for that is just the type of the returned expression. And that is case body dot get returns. That gives us an expression, and then we can get the type. Okay. Yeah, let's maybe not turn that into a, let's turn that into a list instead of that, and let's just push something to the list, and then the common type is going to be the union type of those case types, plural. Whew. Or if there is none, then similar to what until now we did in here, is we will, hang on, cast args, stuff. Hang on, we have a switch. So what we do is we do some stuff. The condition is compiler lookup of the condition, sure. Other stuff. Oh yeah, this is important. And this as well, yeah. It is weird. I don't like that I'm kind of re-implementing that, you know. Well. I really don't like that. Well. Yeah, that's gonna be body dot get condition dot type. Yeah. Then we have a common type, which will be the union of all types. And at some point, hang on, yeah, here we do this basically. Then we add cast expressions, but in a more elegant way than even has the same name, case types. Yeah. Okay, yeah, and then what we do is we, yeah, kind of add casts there. Okay, but one thing I don't like. One thing I think I'll keep simpler in the egg than in the yogurt is that I don't want to have cast functions yet. Which makes sense. We don't even know, like, it only makes sense to compile casts into functions for concrete types. Here we don't have that yet, so instead I think we'll just need some sort of cast expression in the egg, which is defined in another file in here. So let's add some sort of cast expression of some egg ID, and the type of that determines what type that ID is cast into. Yeah, that's more elegant. Okay, so we have these. We have a common type, and now we want to build cases, which will be this kind of thing, but not exactly that. So cases will be a map from string to, well, to a body. Yes. And basically for every compiler in case compilers, we basically check if, well, hang on, let's just add a cast expression either way. And I think we're moving cast expressions from the same type to, like, from one type to the same type. And we can remove those in one single pass, and then we don't need to special case for that everywhere we might need to insert a cast. Okay, so for every compiler in case compilers, that gives us an entry with a key and a value, which is a tuple with a actual type, I guess, and that would be the compiler. So compiler dot value dot b dot get compiler dot value dot compiler dot value dot a get compiler. And that is the ID. Return ID, something like that. The symbol is just the compiler key. The return ID is that, and then the compiler is actually just the compiler value A. So the actual type is that. And then what we do is we insert a cast expression. So we basically do compiler that push something like that. Please push a new expression to that. Namely the expression kind dot cast. Please cast that actual return value to the common type. Yeah, we don't need the actual type, which makes things easier. You know what, let's inline that, sure. Yeah, and then we can do cases dot put into compiler key. Oh, I don't like that. Yeah, let's maybe do that after all, you know. And then just do cases dot put symbol compiler dot finish of the actual return. Yeah. Okay. Yeah. In the end, we have this switch expression that contains with the common type and this source. Yeah, this is fine because this doesn't need to introduce a new expression. This just returns an ID. We have the params. Why do they have name? Like, why do they need names? The egg lambda. That is kind of weird, to be honest. Egg lambda has params, and those have a name and a type. Let's not do that, actually. You know, let's just have an egg body which contains params and, well, and other stuff. Yeah, we don't need an egg lambda. This will just be an egg body. Simple. Yeah, so lambda body is this. And here we push new parameters with these types. For each parent, we get the name. The type is going to be, you know, converting that parent to a type. And then we do visible.define. Sure. Yeah, let's do something like that. Sure. Okay. Yeah, and the lambda just contains the body, doesn't need anything else. Of course, the remaining question is what's the type of this thingy, you know? And I think that will just be the yeah, okay, let's build up some param types, I guess. Which will be a list of plum type. And then for every type, what we do is we do param types, push a type, returns something, yeah. Return type is lambda body dot get returns dot type. Okay, and then in here we say we have this lambda. Let's do some stuff. But what do? We take, hang on, lambda of this lambda body. Not exactly sure about that. Let's, yeah, we need the lambda, some sort of lambda type for that. Something like this, a plum type dot lambda with a lambda type with args, which will be a slice of plum types. So this will be types to slice and a return type, which will actually be our return type as a pointer. Well, you know, yeah. Cool. Okay, yeah, I think I like that. Plum type dot lambda of lambda type. Second argument for the variant. That is weird. A weird error message. Oh, yeah. So we have some sort of map from string to a tuple. And the string, oh yeah, we try to put in an ampersand thingy, an ampersand compiler mutable one. Well, yeah, let's actually just store mutable compilers here, because why not? It doesn't really make that much of a difference, I think. Yeah? Maybe it does. maybe it does. Yeah, let's not do that. Let's be like case compiler. So what do we, here we use that. Let's do that maybe. Oh yeah, case type stop push doesn't need the symbol at all. Indeed. This is just an egg ID. Beautiful. Beautiful. So the function field is missing. True, we haven't gotten to calls yet. So we have this, we have lambdas. Yeah, we have, now we're at calls. Okay, so this is going to be the interesting part actually, where we kind of need to look for a matching function. And what's going on here? We take the call up function. Oh man. Oh, I see. So the thing we call that must be a name, or otherwise we assume it's a lambda. That makes sense. Okay, yeah. It is either a lambda or it's a function, basically. And I think we can actually differentiate among just those two things first, and then we can do something else. So I want basically some sort of enum that is either a you see, in Plum I would just define an enum on the fly here. It's kind of difficult to do in the toast. Oh, I mean, I could make this into a result kind of thing. Yeah, sure, why not? If it is a name, then we look up that name. Okay, you know what, let's turn this into is lambda. I think that is fair to say. Oh, okay, function name, some string, find the function name, either some string, if it's a function call, or none if it's a lambda call. Yeah. And if there exists this thing, if that is visible, then it's just going to be none. Otherwise, it's just going to be the string like that. Yeah, if the thing is not a name, then lambda. Yeah. Okay. And then we have kind of unified this case right here, the expression kind lambda, and this case down here, also expression kind lambda. Because what we do in the lambda case is we just convert the function to egg. Even if that's a name, we just compile that. Names also just by default get converted, get compiled into a lookup. Whew. Okay, yeah, lambda type then is going to be body get lambda, like that, and then we can take the return value, like we just say body dot push an egg expression kind lambda call, which will be an egg lambda call, where the lambda is that, and the arguments we have them right here, and the type, oh hang on, check that argument types are compatible. This is actually important. Okay. And the type of that thing will be the lambda type return type. Yeah. While the source of that is the call up function dot source, something like that. I hope there's some function to compute a source. Okay, so this doesn't work. This is not a variant of plum type. Yeah. Okay, yeah. Lambda type is that, or if that's not a lambda, then we just return an error like egg ID error, or try to call non-lambda. Oh, I see. So let's just do that and then say okay, cool. Hang on, which error string? Okay, yeah, I think this needs a second thing. The source. And yeah. Oh, that works. That's nice. What's going on here? We have the, oh yeah, the return type is a pointer. Yeah, let's dereference that, sure. Now, yeah, this evaluates to an egg ID. That is true, and that is correct. For the case where that thing doesn't evaluate to an egg ID, we want to do something else. We basically want to do this. Yeah, we don't need to build to get candidates. We have candidates actually. We have, oh, I don't know, visible, I guess body dot something. Body dot funds in scope or something like that. And we'll need to do something very similar to what we do for calls in here. Actually, we probably kind of want to move that calling into the other compiler stage. So we have the arguments. Yeah, now we want to get those argument types like that. Archetypes. Yeah. Oh right, this also exists. Oh man, yeah. All of that gets moved over. So what we do here is we build some sort of expression, okay, by looking up a function and then casting that and doing stuff and pushing a result. Okay, I'm just going to copy that over here, and that is going to be messy, I think, adjusting that and, like, you know, yeah, adjusting that to the current, to the egg. I think I'm actually gonna take a walk, maybe. Well, okay, this lookup can attend to what's actually doing that here in line. Yeah. Yeah, it's not super long, I guess. we'll need a concept of some sort of X signature. Yeah, let's make it so that the egg actually contains not a list, but a map of functions. Where the X signature just contains the module, the name, and the parameter types. Yeah. Something like that. Okay, so hang on. Fun has params. Yeah. Let's turn this into that, maybe. No params, which are just types, and return type. Yeah. Param types, I guess. Yeah, but then we don't need this. We can just do that. Okay. Then we do that. Yeah. cast the arguments. Yeah, so we look for args.iter and find the params.iter, param types.iter. I think this body. Yeah, we don't need to do any like comp time cast or something. Although we do, I think we will actually have to do some sort of comp time stuff. Well, this is getting a bit out of hand, to be honest. Like basically we're kind of reshuffling what goes into the egg and what goes into the yogurt. Okay. I think I'll go on a walk, actually. Just to get outside. So the cast argument is the argument. Oh, this is weird. This is really weird. Yeah, I guess let's not. Let's introduce some sort of comp time thing in here, because I think that's actually what we need. So this will be comp time value, and this concept of a yogurt value, this right here, will actually be does that? I think that doesn't even need to type, actually. Nope. I think just having that is enough. Oh man. So this is an egg value that is either an integer or a string. So they don't need to be up here. Or a struct. Or an enum. Nope, hang on. The lambda. Nope, the lambda contains. It directly contains a body, right? So yeah, it captures stuff. I think that would just be a map, I guess, from egg ID into some value. And then it has a body that then has explicit other parameters and stuff like that. I mean, this is weird. It makes sense, but it is weird. Yeah, okay. Yeah, let me go on a walk and think about this a bit more. My voice is kind of shit, so I'm not gonna talk. And just drink some tea. Yeah. Okay. So I'm not gonna talk. Just if you want to watch me code, do so. Yeah. should you be able to overload types. Okay, I have two types with the same name, but a different number of generic arguments. I think you should. is weird. Intuitively, the first step to doing this in a clean way is just, having this global map of all types and functions with unique signatures. And then imports and exports become as easy as a list of X signatures, that a set of X signatures specifying which of these actual functions are in scope. Yeah. And I think these are shadow. So types are not really, fully resolved. A toast type. Yeah. This is super weird. I don't like this at all. I don't like this at all. Let's do stuff like exported funds, maybe. here let's do funds and scope. And then let's do the same thing for types, basically. Types and scope will be a map. We'll return a map from string to... Oh, hang on, nope, I think you should just be able to say give me a type with a specific name. Oh. Then again, I'm not entirely sure. Types and scope. Well, let's do stuff differently. Let's say types in scope maps a string. Yeah, let's say for now types don't have overloading. You can't define different types with the same name but a different number of generics. So types are just a map from string to some types. Well, not really, because really they are a string and that maps to a plum type with also parameters, so it's really like this. Several parameter that this type needs, and then the actual resolved defined type. Yeah, this is so weird. This is so super weird. Okay. Anyways. What do we have here? We have the we have something like this, right? Types and scope means we build up this map. This is a mouthful, but sure. Then for every definition, if that is an import, then we import that. If it's an export, we don't care. If that's a function, we don't care. If it's a type, then we care. You know, if this is a type, then here we put in the type name and a tuple that contains, I don't know, the type somehow. This is weird. This is super weird. Oh man. This is a horrible, honestly, horrible type. I mean, look at this. It's almost the entire line. I don't like that at all. What is a toast type? Oh yeah, this is a toast type dev with a name, with params, and then a toast type. Okay, so it has a name, it has params, which are like names and stuff. Oh yeah, horrible. I don't like how this is going. So I want to build a slice of long types. Variable doesn't exist there. Well, that kind of... Ooh. That makes things difficult. Yeah, I want something like this, actually. I don't know what to do, to be honest. Thought I could make this more beautiful. Because now we basically want to already know which functions exist and which types they expect and stuff like that. So I feel like even before compiling the toast to the egg, we need this kind of a really small intermediate stage that has this global mapping from signatures to stuff. And then we can have, for tracking which things are in scope, we can then just check these signatures and build them instead of relying on def in scope, which is which originally I think contained the egg fun directly, which we don't have yet because we built this up piece by piece. So like this seems reasonable, asking which functions are in scope, and you get back, boom, a slice of signatures. That is super cool. I don't know what to do. Maybe I think having something like this makes sense. At least for functions. For types, I'm not entirely sure. Maybe this, I can remove this, yeah. But even for types, like imagine you have two modules. One defines some type foo, and then the second one defines a type bar that depends on foo, importing that module, you know. But then the first module also defines a type baz that depends on bar. How? I think currently we don't handle that, because we can't just ask, you know, what are all the definitions in oh, I see. Yeah, okay, so we have toast type defs, and this is also what we had previously. Yeah, toast type def. I don't know. Maybe something like that. Okay, so can we maybe ask which signatures are in scope without resolving other toasts? I think that should be possible. That should just be a slice of signatures. Every definition we just say if it's a type, if it's a function. Well, if it's a type, then we add. I feel like I wrote this somewhere already. Here. Well, not quite, but almost. Okay, so for type, we just say, well, this type is now available. function, we say this function is now available. So the module, the name is the function name, and param types are the function parameters. Here I feel like I already messed up. Because the parameters, they are not resolved yet. Oh, why is this so horrible? Okay, so we have some sort of prepare for the toasts. Okay, we add built-in functions. Fair enough. And then for every toast, what we do is we check which definitions are in scope. If it's a type, okay, so to our global list of functions, we add this toast fun. That makes sense. And to our global list of types, we add this type. Yes. This is horrible. Horrible. Let me review the code. See how that was before. Because it worked somehow. So for asking which definitions are in scope, we simply asked what are the exports of the imported module. Exports, okay. So we ask for exports. And if that module contains some definitions, just don't allow circular modules. Like one module importing in another, and then that module imports the first one. Maybe. But it does seem useful. Yeah. So what would that do? Like, this would just push def in scope. So if we ask for the exports, what we do is we go over the export thingy, and yeah, we ask what are the defs in scope. Okay, so circular modules just don't work currently. Interesting. Interesting. That is not how I want this to be. Okay, so how do I want this to work? Basically, yeah, let's have these self-contained types, type definitions, self-contained. Self-contained function definitions. Problem is, yeah, like I think first we want to just have a map of all types from all modules. Then we want to build, some sort of map for looking up types, where you can just, if you have a, I don't know, complicated game that contains a player type, that contains, that has a list of items, so it contains a list type from the standard library, and that one contains other stuff. And basically I want a map that maps every type to just raw plum types, a map for that. Once we have that, then we can continue with looking at functions and seeing, just lowering the signatures of all functions, seeing which functions are in scope, stuff like that. Yeah, that does seem useful. Okay, so basically, map of all types, something like that. And what we want is some sort of map. We want to pass in a module and a toast. Well, no, actually, this one right here. And that should return a map from string. Nope, from a tuple of string and module and string to a plum type. And that should allow like circular types across multiple modules, stuff, anything, you know? So the way we do that, I think, is we just build a map of types where the key is just more fundamental. You should be able to get exported types of some toast. Okay, now let's go over all. Types. We just say, let's get the toast. We go over all definitions, and if that's a type, then we add a key into this map. Okay. Just that, nothing more. You know, types.put. The key is going to be a tuple of the module and the string, and the key is going to be the definition. Okay. Yes. And actually we do that for every module. Yeah. Okay, so now we have a map from module and name to the toast type definition. Beautiful. Now we can convert those toast type definitions into actual plum types. And that needs recursion, because the one type definition can depend on another type definition, which can depend on another one, etc. So we just have this as an argument. Type defs. And we can compile a type consisting of all of a name and arguments and using these type defs we should be able to compile that type to a plum type. Look at that. And And then in here, the only thing we need to do is create another map, very similar to the first one, except now these are compiled. Very cool. So what we do is we just say for each type in types, what we do is we compile that type Okay, so the question is, what if this type contains arguments? And that is actually a very good question, because I don't know what happens there. I suspect we want to... We could create some sort of plum type that uses plum type.primitive with like a 0 or something like that. To kind of notice how here should, like a type should be inserted here. Something like that. Yeah, I think that's fine. Yeah, okay. So what we do is we do compile types.put type.key type.value.compile. Okay. So now we have the module and we have a toast type def. Okay, so this is a toast type def. That is nice. Toast type def. Toast type def has a name. And actually, you know what, let me maybe make something like type signature consisting of a module and a name, but later on maybe also the amount of parameters that they take. Okay, yeah. So what we do is we have this. Yeah, and these right here, these will just be type signatures. Oh man, oh man. Yeah, type.value.compile. And now we can basically check we want to compile a toast type def. What do? We know our current module, we know the definition. Let's compile that. Should be doable. What we do is we need to check which types are in scope. In this module. Yeah, that returns a type, a slice of type signatures, where each type signature, how do we do that? type signature. Refers to other types somehow. So we need the toasts to figure out which types are in scope, definitely. So what we do is we do this, basically. Yeah. We just build a list of type signatures. And then for the module, so toast get module dot defs. For every definition in our module, we check is this a type, then we do something. Let's actually switch to that. Because if it's a type, then we have this type in scope. Type signature of that module and the type name. If that is an import, we also have something in scope. Well, we need to figure that out. But the important thing is for the import, we don't need to traverse down into the other modules. But we can just do something like this. For every part in the import part, we resolve the imported module. And then for every name in there, we just claim that that exists. So hang on, for def in imported module, the export. Yeah, no, we don't need to do this. We just say this right here. Oh, we have a new type in scope because we import that. And yeah, this will also match functions, which is kind of weird, but man, there should be no conflicts with names. Although I'm going to add a to-do here. Yeah, we have the module. Oh, hang on, the module is actually the imported module, and we have the name. I will do that from there on. Oh, yeah, filter out functions. Okay, yeah. So without looking into any other modules, we can just say what types exist. Hang on, do we even... Oh yeah, we need to know our current module so we can resolve other modules. We do not need all toasts. Our toast is sufficient. This is our module, this is our toast. And we go through the toast, we see, oh, there's a type. That's a type that is in scope. There's an import, okay, so all imported thingies are in scope. Nice. Okay, so using that, we can now compile a given type definition. I think we can. Yeah, this also needs toasts. I'm just realizing that. Because this asks for the types that are in scope, which will be module.types in scope. In our toast. And then now we have all the signatures of the types that are in scope. We could then use these to resolve our type definition. Not compile, let's call it resolve, maybe, you know. Because at least to me, compilation implies something like heavyweight, compiling runtime code or something. The types, they are just aliases that get kind of desugared, basically. Okay. So we have this, we have the types that are in scope. So now we can look for one that matches our type. Hang on, you know what, let's actually also store the amount of I'm not sure, the amount of parameters, something like that. You know what? Maybe not. Maybe not now. Okay, so first we're like, there is no type. Oh yeah, hang on. We're converting a type def. Yeah, I think let's instead do this right here. We try to resolve a type with this name, with these arguments, which are plum types, in this module. That's basically what we're saying. Oh man. So we check which types are in scope in this module, giving us type signatures. Then we try to build a type by going over all the types in scope. Well, yeah, over all of the type signatures that are in scope. And for each of these, we check if it matches. So basically, if the name is the same as our name. If that's the case, this is definitely the type that we want. Yes. Yeah, so what we do is we have the arguments, we have a type, But I know that I'll also add functionality for directly lowering a toast type def. In this module. And toast type def. Oh, toast type is what I want to lower. Yeah. Toast type in this module. Okay. Oh man. So please resolve this toast type with, I guess, substitutions. Maybe not. Anyways, what we do is we switch on the type if it's a variable. Let me copy this to here. Then this will just become a plum type dot primitive of that variable. It's not really a primitive type. I probably should rename this to like named. I don't know. Yeah, if it's a call, this is interesting. Because now we call resolve using that name. And these arguments. So lowering args. Arg is a toast type. Yeah, so it needs the module type def toasts. Yeah. Resolve of that name and the arguments. And the module, the type defs and the toasts. Yeah. Okay. Next. Struct type. Right, we need to do that somewhere, right? Combining types. Here. So there is a lot going on here, which is fine. I'll take this as inspiration for this up here, because this will be pretty much the same. So for type variables, we just yeah, no, we don't do this. And we have this env, this environment down there. What does that do? Because that seems useful. Maps string to plum types. This is super cool. Let's use that up here. So we want to convert a toast type using this environment and this module. These are all the type definitions. These are the toast types. Okay. So case variable, in that case, yeah, we want to do this. Yeah, okay, so this must return a result. Also, seems reasonable. If this is a call, then here we do crazy stuff. We lower the arguments, which makes sense, yeah. Oh yeah. Oh yeah, this is actually... Ooh. I don't know what to do there. Okay, yeah, I'm just gonna use this down there as the as the baseline. here we just call to add with our in scope things on the custom type. That is not correct. The previous code was broken. I'm sure. I'm happy. I'm kind of reworking that. You know. Damn, this is a lot of stuff that gets carried around too. That kind of sucks. Even before resolving types, can we maybe just get a map of the types that are in scope for every module? I think that would already make a huge difference. So, types in scope. In this module, give this toast. Boom, slice of type signatures. Why is the analysis so broken? Doesn't make any sense. 43. Okay, maybe it is not broken. Well, yeah. We have the in scope. Okay, so to get the map of all types, module and toasts, we build this map of all in scopes. Oh, in this scope. Maps, I don't know. Is a map for each module which types are in scope. So then for every single type, every single module, we don't need that. Basically ask the module which types are in scope. This is more of a list, all slices, but types, let's rather call this like defs, maybe. In scope dot push, I think. Okay, so here we have all the modules. Oh, we could, yeah, let's do that. Let's put that over there. We'll merge these two. But then again, no. they don't have to be linked, so let's keep them separate. Okay, yeah. Okay, so now we have basically for every module we know which types are in scope, the signatures, and we know which for each signature in general we know which type definition that is. That is already pretty cool. Now we want to be able to resolve individual types using some environment, yeah, and basically, knowing which types are in scope. Which will be a slice of toast signatures, or type signatures, yeah. And then, because we'll kind of recursively look at other type definitions, we'll also need basically this right here in scope lists of other modules. Not the original toasts, but we do need the defs. Yeah. Okay, this is amazing. So for variables, they need to be in the environment. Else, interesting. Same strategy, yeah, I guess. You know what, let's turn that into an error actually. Yeah, I think that should be an error. Yeah, this kind of thing. Amazing. And the source of that is the variable source. Okay, yes. Whew. Piece by piece, we'll get there. Okay, if there is a call we'll get the name, we'll lower the arguments, we'll check if we are recursively lowering a type. then we go through the definitions that are in scope. This one right here. Yeah. Oh, and these are actually only type definitions. So this code gets simplified because it is definitely this. Yeah. So for every definition in scope, we just switch on the definition if it's a built-in type. That matches, I see. Yeah, then we just return. Oh, hang on, in scope. In scope was a list of type signatures. So we just need to do if def.name equals name.string. Then we'll take the, well, the signature contains, we know there's signature matches. And what we'll do then is we'll take, oh, hang on, this is more like a signature. Yeah. Then we know which module that's coming from, and we can get the corresponding definition. So we can do defs.get signature to get the toast definition of that type. That is pretty cool. That is pretty cool. Oh man. I think we'll just do yeah, we'll call this basically. But then again, I'm not entirely sure about that. Built-in types are not handled yet. Okay, so we switch on the definition. If the built-in thing that doesn't work, if that can't be expressed currently. So I'm just gonna comment that out. It is always just a type. And yeah, the name matches, like we don't need to check that, we have already done that. Hell yeah. Okay, yeah. So we just build up this inner type environment. Which will be a map from string to plum type. Okay. So check how many parameters that definition needs. That has to match the number of arguments that we want to provide. Amazing. And then we put them into the map. Makes sense. We push something to our parent calls, which doesn't really make sense. That doesn't exist, you know. And then the type, oh, I see, the type behind that definition, we're gonna resolve that with the inner. That is pretty cool. That's pretty cool. Yeah, and if now no type matched, then we do that. Nice. Very, very nice. We do need to handle parent calls and depth, so the signature is gonna be even more crazy. Yeah, this stuff. Oh, it's a list of ongoing type call. Yeah, that makes sense. Okay, yeah, cool. Yeah, I think that these should be pretty obvious. Let me just quickly check. Yeah, we have the call. Okay. So for structs, we just lower the fields. Yeah, using the in scope thing. Oh, hang on, this one is not correct though. Yeah, this will be in scope lists dot get signature module. So basically, if we compile, let's say we have a module and there was some list type defined there, and then we use some import some type foo from some module, and we use that. Then within that type foo, within that other module, list may mean something different than here, and then we want to use that inner module's list definition. So the in scope types from that inner module that we're going to use. Oh man, okay, yeah. And using the inner env, yeah, makes sense. And we have what? That's crazy. We have a definition, we have an environment, we have the scope, we have in scope lists, we have defs. And we have the type, we have an inner env, we have in the things that are in scope, we have in scope lists, we have the defs, and then we have parent calls and depth. Damn, that is a lot of stuff. Okay. Okay. Very nice. Yeah, here arg.resolve. No, this is what is this even supposed to be? You know, we need more stuff. Yeah, this will just be in scope, to be fair. scope lists. I think this is not correct. So if no, I think we need to first substitute the signature, the type, and afterwards lower the arguments within that type. Yeah, because if the depending on this type right here, we don't know how that call, what that is shorthand for. So it may put the arguments at different depths within that inner type. Meaning this, just putting recursive types in there doesn't work. Oh man. This is kind of crazy. Yeah, so we should do this after the where do we use the arguments here? Environment. No, that is not correct. Man. This is so much more complicated than I initially thought. So much more complicated. Damn. Like what? How am I even supposed to do that? Damn. Yeah, I guess this definitely deserves its own, like, types. And types may span multiple files, modules. From multiple modules may as a first step. Build a map from okay. Mm-hmm. Man. Look at those arguments. That's crazy. Okay, I think I need to kind of fundamentally rethink how I do this. Because the current approach just doesn't cut it, I think. This doesn't work. Not at all. Okay, intuitively, let's say we have some types. We have a type foo that is defined as whatever, you know, bar of int, and foo itself has a t. Yeah. And let's also say we have another type that is recursive. So this is, let's maybe do this first. This is, you know, our linked list, which is either empty or it contains an item and more stuff. So hang on, that would be an item and the rest. Would be a list of two. Okay. Whew. So now if we have a type foo that is a struct containing a list of foos. Oh, wait, hang on, a struct with x and y with things inside. What we do right now is we see, okay, we want to lower foo. Okay, this is a struct type. So we compile this int type. We compile this type, we see, oh, this is a call. And for compiling these inner types, the depth is 1. So that means we compile this foo thing. I mean, I guess the thing I'm noting is we can't just compile this foo independently from the list. We have to first desugar this one right here before we can tackle this one. So the current logic is wrong of first, you know, doing that. Oh man, I guess let's try something really simple, really simple, which is let's try rewrite rules. Okay, so first of all, let's decouple the scopiness of types from the resolving of types. I think that would make code much easier. So the way I'm gonna do that is in scope lists. Hang on. What do we do here? We have these modules to the type signatures that are in scope. And And here we just have the definitions directly in here. Okay, fair enough. I think the first step would be to kind of rewrite these definitions so that if there's a call in a definition, a type call, then instead of the name being something that is supposed to be relative to the current module, current for whatever current means, this would need to directly refer to the module and the name. My point being is rewrite those types first of all, so that there are no naming conflicts and types are resolved and stuff like that. It's all immediately fine. Yeah. Let's do, not entirely sure to be honest, kind of rewrite, like rewrite type. Horrible name for that, but that's the way it is. So this will take a toast type and return another toast type. We'll switch on the toast type. If it's a call, oh yeah, it needs these right here, these in scope lists. It needs to know which types are in scope, first of all. And then it does and if there is a call, then this will be mapped to a toast type.call with a name and args, but a different name, a different args. So the name right here will contain the module of the type we want to call. So we actually need to figure out which type we want to call here. That makes sense. That would be, where's that? Where is that? No idea. In scope. Where do we use in scope? In scope lists is something we have, but the in scope thing. Oh, here. Oh, okay. So we look for signatures. Yeah. For every signature, if the name matches, then that's the type we want to call. So we replace this call with the module followed by the name. Crazy, I know. And what is that? Yeah, it also has arguments, which will be which we'll have to rewrite as well. Like prefix with a module, something like that. Yeah, args will be a list of toast types. And then for every argument in the call, args, we just say argument, hey, please prefix your calls with module in the current scope, in scope lists. Okay. We've rewritten this call with a toast type call. I think that makes sense. Maybe let's use double colon here or something. Something to make this like a dot. Yeah, let's just use a dot. I think that's cleaner. Yeah. Resolve refers to ongoing type call, but that type doesn't exist. Yeah, okay, sure. Prefix calls with module. Make unique, maybe? I don't know. Okay, let's see. Types in scope. Yeah, and after that, after we've prefixed these calls, we don't need to do anything more. Anything more. That makes things a lot easier. So I think let's actually do defs is this, and then for every one of the module we have the toast, and for every definition in here, we check is this a type definition. It turns into a string. Yeah. And let's actually switch on the definition. Okay, so if the definition is type definition, then in there we just put the signature. Yeah, but that's just the module dot and then the name. Boom, simple as that. But also, if this is an import, then we do stuff very similar to what we do up here, and then we can remove that part up here. Yeah, all of that. Clean. Hell yeah. So if this is an import, then for every part in that import, we basically check the imported module. Okay, fair enough. Like that makes sense. Yeah. Yeah, and then we kind of need to filter out functions. So I guess for each name, we just check if name dot is uppercase, something like that. If name dot Charles get then this is a type. And now comes the cool part. Now we just say, well, this is basically a new type definition. If you put an import in your code, that is like a new type definition with a new type name, you know? The current module dot, and then the name. What's the definition of the type? Well, it's just actually calling the other type. So the definition is just a, hang on, what is it, like type, oh, hang on. Do we want this to just be a string, or to be a string and oh yeah, the length of things is unique, the length of the arguments, I guess. Yeah, anyways, we're basically defining another type. That is just a toast type call of this other modules type. Oh, that is nice. Where the name is an imported module dot name. So it's like defining a type alias in your module. And that is pretty cool, right? And we need to figure out like how do we map parameters and stuff like that. But still, we just do this once. We don't need to worry about this. We just have this map from string being like a very, the type signature containing the module and the actual type name to a toast type. And once we have that, now we can iteratively replace types without worrying about like naming conflicts or which types are in scope and in scope lists and stuff like that. Just focus on resolving types. Yeah. And here the problem was that this is a recursive type, but if we, before resolving this call, if we lower the arguments first, we use the current depth. So if this right here would do something like, oh, the rest is not a list, but it's actually a struct that then contains a list. Depending on how many nestings there are in here, this T right here, this if we inline this right here, this foo definition, like this, oops, no, like this, and T being foo, this right here needs to be replaced with a recursive type -1, and this one with a recursive type -2, or something like that, So we can't resolve foo first and then basically pass that to the call, insert that into the call, because our recursive types are represented as the number of levels that you jump up. So rather than that, we need some sort of rewriting mechanism where we see, first let's replace list with this, and then you're pasting foo as kind of like a new type in there, but not say, well, this is the type 1 level up, and then replace that list type, T being replaced by that, because that doesn't work. Now this does something really wrong, really wrong. Yeah. So that's horrible. Yeah. Okay. Resolve. Type. Oh yeah, this type right here. This needs to call this prefix calls with module. Oh, this is clean. We don't even, like, first of all, we don't use these except calling ourselves recursively. Let's get rid of that. But also, we can just use the module directly like this. Yeah. Damn. Okay. So we can just do for every. Nope. Not even this complicated. Not even that. We can do things even simpler. Just this. Mapping the arguments of our module. And this right here will just have the module and the name. We do need to handle the other cases as well. So yeah, name and args. Oh, this is clean. Amazing. Okay, so let's maybe jump into toast type. It can be a variable. That's going to map to a toast type, to the type itself. That's it. Nothing more to say about that. We have the call. We have a struct where we basically build this map of fields. And then for every field in struct directly. Oh, it's a slice. Toast type field. Which has a name and a type. Very similar for the enum. Yeah, but atlas. Okay, and finally lambda. Ooh. Okay, we did that. That is pretty cool, to be honest. Let's maybe move that up here. A map with module prefix type names. Yeah. Prefix calls with a module. Boom. Call, stuff like that. Amazing. Honestly amazing. And then we do other stuff. Something like that. And for imports, we basically define a new type. Amazing. Yeah, we should filter out functions somehow in the future, sometime. Yeah, and then here we just push a new type definition with a new name and the args. Well, this is the weird part. For now, it's just going to be an empty slice. That's not correct, but yeah. So empty slice of, what is it? Plum types. Is it plum types? No. Args toast call of toast types. Makes sense. Yeah. Okay. We can do this. So now we have a map of mapped types. Crazy. Honestly crazy. So this would yeah, okay. Yeah. I see that. We have a good now, instead of toast type defs being scattered around in toasts, we now just have defs, which is a map from string to a toast type def. Simple. Really simple. Okay. Next up. Resolving types. That would basically mean kind of rewriting types until there was no longer any internal until there no longer exist any calls except of ourselves, basically. I think something like that. Yeah. Yeah, so let's do that. Let's say expand calls, something like that. Yeah, so this will just be a map from string to plum type. Yeah. And for every value, we're gonna resolve that. And like this is very high level. Instead, let's maybe expand this. Expand, yeah, with some sort of recursion anchor. The recursion anchor being the key right here. Some sort of recursion anchor, which will be a call. Yes. A toast type call. And in this case, this will be the toast type call, where the name is the def key and the args are the def args. Oh, hang on, the defs don't have args, I think. Oh, I don't know. Let's say this is just the expanded one. Yeah, I'm gonna take a break. All right, yeah, expanding types. We have the recursion anchor, which is a toast type call initially of the definitions key. And then we also need, oh yeah, basically these definitions right here. So a map from, what was it, string to toast type. And that should result in another toast type, I think. Okay, so we basically switch on that type, similar to what we do up here, basically. Let me just copy that. Yeah, so basically if we have a type variable, hang on. Yeah, we also need an environment, which will be a map from a string to toast type. And we'll need the parent expansions, I don't know, parent calls, something like that, to guard against infinite expansions. So we have this type. If it is a variable with some name, then what we want to do is we want to get that variable from the environment. And it should definitely exist there. There's no question about that. So env.get is the correct thing to do, I think. And how's that? Oh yeah, up here we just ignore that, I guess. Env.get variable dot string. I suppose that's like a string and source thingy. Yeah, that returns us a new toast type. Fair enough, yeah. okay, and we just return that. Okay, that seems fair, I think. Yeah. Then here we have a call. Well, if that call, oh, there is no equal for that, I think. So we just check, I guess, if call dot name oh my call dot name dot string equals anchor dot name dot string, and well, call dot args equals anchor dot args, and then we just return. Otherwise, we kind of extract the name, we extract the arguments, we extract the name, we extract the arguments. Yeah, we expand the arguments. And then this entire thing does not just result in call. No, instead we just call expand on the call's definition. So def.get call name. Oh, can that fail? I think it can. Maybe. Yeah. So this should return a result. Also for recursive types catching that. So defs.get call name. So this will be get maybe. Called def is that. Or if that doesn't work, then we'll just return an error. Hang on, no, recursive types are fine actually. Oh, yeah, just this is, try to call, try to use, I don't know, call name, a string, I guess. That type doesn't exist. Amazing. And then call name.source. Amazing. Okay, so we have the called definition, and then we'll just do call def.expand, please. I'm using, yeah, I guess, like this. I'm using the environment, hang on. Oh yeah, we need to build an inner environment. Duh. We have some sort of, yeah, the anchor stays the same as well as the definitions. So we'll just say expand that with the inner, and the anchor stays the same as well as the definitions, and the and let's maybe resolve these first. Yeah, here we can just do that, and then we can also check if like call args.len should be equal to call def dot, we have a definition, but that doesn't, tell us how many type arguments that has. That is weird. That's super weird. No, this is really weird. Maybe this should be a toast type def. Yeah, I guess. Yeah, yeah, so this would just be a toast type def. Defined using a call that stays the same, but it also has a name, of course. That will be the module's name, and it will have arguments. Something like that. And then we do this. Yeah, expand. Oh, expanded is such a nice name. Hell yeah. Okay, and in here we just I'm realizing always getting distracted by other stuff. I forgot. Yeah. Amazing. Yeah, then we have the arguments. We expand the inner environment, which we built in here, by the way, inner env, because that will just be a map from string, to toast type, and here we zip the called def args with the actual arguments that we provide, so that we can then put that in the inner environment. What type we have the env. And then called def.expand. Yeah, amazing. Yeah, this is nonsense. Very nice. And that is what we return, wrapped in an OK. This will be pretty similar, right? Expand with env anchor and defs. Yeah. Okay, yeah. Cool. So we can expand these types. using that, we can now do something even more advanced, which is generate a map of all types by creating all the definitions, prefixing calls with modules, stuff like that, creating these kind of virtual types for imports, these kind of proxy types that just forward the type to this modules type. Okay, yeah, and then in here we have the expanded definitions where we just expand the type, yeah, with some environment, which will be from string to closed type. Yeah, that will just be for param in def.params, and here we'll just put the key and the, well, you know, the closed type dot, oh no, params is just a list of strings. So we can do that. And this needs the env, the anchor, and the, oh, is it args? Maybe it's args. I don't know. Yeah, env, anchor, and the defs. Okay, so now we have expanded definitions. That is pretty cool. Ongoing type call, that's not, like, why, hang on. Why do we have ongoing type calls? Oh, for recursive types, I guess. However, we don't really need them. No, because we extend everything all the way and then only stopping at the anchor and then doing stuff. Yeah. So I guess this, I'm just gonna comment this out. Same as this, same as this. Oh, this is nice. Yeah. And yeah, I think like there are definitely things that are not working yet. No question about that, you know. Ongoing type call. I just want to basically comment in this toEgg function for for this one, this one, exactly this one, and this should just be like a to-do. And now it should only report syntax errors and nothing else. Okay, yeah. You're writing egg. I think here we would have functions. with keys. So some sort of that. Param types, right. Oh yes. Instead of this, you just have time. I'm not sure about this. I think I'm just going to not care about indentation here and not put any new lines here, but instead just put all fields after each other. Yeah. Oh yeah, cast. Cast is interesting. Not really. Fair enough. Body is not a feel on egg body. Okay. I guess that is true. I see, so we don't need this at all. Just do that. Boom. Simple. Yeah, okay, egg to yogurt, I'm okay with that failing, you know? Like, I wanna be able to do everything up to the egg. The part after that, I don't really care about that. Okay, so there is a to-do and there's to-egg. Oh yeah, that makes sense. Because there is nothing else here. So let's maybe call some of the type stuff. Why not? Resolving types, yeah. Let's call map of all types. Yeah, it's posts, not the debug, but this one. I don't. Indeed. And that is by design. So probably just without underscore. Yeah. Need more stuff. Prefix calls with with module, probably. No, hang on, that just needs a module, I think. Oh, I see. Like that. Oh well. Yeah. You actually need a toast type ref to put in there. That then has a name, which will be def.name. We need params, and we need the type. Oh, hang on, this is a type. Ah, yeah. Yeah, that doesn't make any sense. Just that. Boom. Simple, clean. Toast type variant. No, these need to be toast types. One, 7, 6, was it? 8, something like that. Yeah, return error, inconsistent return types, because this is just a map on. Hang on. Map of all types. Yeah, this should be able to return an error, I think. Yeah, if types don't exist, for example. Or struct types are infinitely recursive, maybe. I don't know, something. Okay. this map of types. That's what we want to return. Yeah, Charles is not a field on string. Okay. Yeah, fair. I think that's a function though. Yeah. String to name. Down here. Oh, the import names don't really have. Okay, you know what? Let's just take the import keyword then. Toast type def. Slice of toast type. Oh yeah, but these need to just be strings. String and source. Also, big to do. Important to fix. Now that's going to be a put instead of a push. Here we basically go over the parameters. Yeah. Oh. Expanded defs. I mean, I can use def dot value, which will be a toast type def, and that has a name, and that is what I'm gonna use. That should be fine. Okay, so expand on a toast type def. That is true. Oh wow. Okay, comparing toast types. Yeah, I think you should be able to do that. Okay, so we switch on the type. Oh man. Yeah, and then we basically, if b is variable, oh, right. Yeah, and if b is variable b, then we'll just check if the strings are the same. Not sure about the source right now. Yeah, if b is a call, and then we need to make sure that the that both calls are the same. Oh, this is gonna be pain. Okay, I guess. If b is call b, then we check that a, just that a equals b. Okay, for structs, if b is a struct, we have two calls. What we do is we check whether the names are the same. And whether the arguments are the same. Yeah, then same for fields, same for variance, same for lambda. Oh man. Yeah, first fields, they have a name and a value. Variance, same thing. And then lambdas, they have, well, they have args and they have a return type. Oops. Okay. Yeah, value is not a field. It has a name and a type. Right. That makes sense. Oh, come on. Comparing to ampersand of close types, I think that should be... How is that not implemented in a general way in the standard library? Library... Okay, but now we're getting back to the actual sensible errors. True, so expand can return an error, which means that every time we call expand, we actually need to unwrap that and stuff like that. call doesn't work. Inner env. Hang on, we have it. Oh yeah, we need a type. Which function expand? Okay, so we are in the expansion function. That's cool, I think. Plum. No, still toast types here. Yeah. Let's maybe also print them. Ooh, this is cool. This shows that we use something like import built-in type, and the type now got prefixed with the module that it's in. So it's now built-in .type. That's pretty cool. That is so amazing. Yeah, so the built-in type is not in the definitions. That may actually be true. So map of all types, we have these definitions indeed, and rather than just going through the toasts, we'd also add a little built-in type in there. So basically for each hang on, there was something in here like type int, type, yeah, this one here. Basically want that. Put built-in module colon type, and the type is, I don't actually know, some sort of toast type def dot something, I guess primitive. I don't know what to put there. Yeah. Toast type def is not an enum type. That is indeed true, because the toast type def has a name, which will be the type's name. It has params, which will in this case just be an empty slice of strings, and it has a type which will be toast type dot primitive. Yeah. Maybe not. What are they called? Variable something. Toast type dot variable. Yeah. Ah yes. With a string, but it needs a string and source. Alright. So this invalid source. Amazing. Same here. Sure. Toast type def. Try to assign slice of string. Yeah. Okay. It compiles. Okay, same error though, so. We see 2 egg main, compile some module, convert that to an egg. Okay. Yeah, that is kind of weird. I mean, expand is only called from here. And the definitions that we pass in here, they are just these definitions. So there should be the, what's it, built-in type. Ability.type, that's should be this. Let's maybe print those defs. Okay, those are some types. Damn, okay. Ooh, that's cool. So the type is workspace call maybe. And it's actually a type definition that, you know, says, hey, maybe, and then maybe of t is defined as being an enum, a variant sum, and the type is actually, the associated type of that variable is just t, and another variant none with an empty struct associated. Amazing. And then there's the workspace test playground.type. Yeah, that makes sense. That is the toast type def. Yeah, oh yeah, because it's imported. So the workspace test playground type is a type that is then has no parameters and is defined as calling the workspace call type. That's pretty amazing. So workspace call maybe calls the workspace call maybe. Then there's the workspace call type info. Workspace call info that calls workspace call type info. Yeah, but all these types, they get connected, you know? That's pretty cool. That is pretty amazing. Pretty amazing. I'm wondering though where the built-in types are. Here's something that looks built-in, I think. Dollar stuff. Here, built-ins string. Nice. We have built-ins int as well. Yeah, let's print maybe one per line. I think that would make things much clearer. So first the key, then colon maybe, and then value. Yeah. Ooh. Yeah, maybe just the. Does I need a debug? Oh, can I say type and then? Okay, so yeah, I'll fix writing types. 1, 4, 3. This only has the type. It's not, no, that doesn't make any sense. It's just the name and then the type and a space in front of that. That's it. Hell yeah. Okay, so these are the types. We have a built-ins int type, for example, a built-ins never type, a built-ins string type, built-ins type. Oh, look at that, built-ins type. I mean, this is pretty cool, you know, just being able to see that. What is it? The playground. I'm looking for some playground stuff. We have a workspace test playground.maybe type. That is just the workspace core maybe type, and that workspace core maybe type is defined as workspace core maybe type from the maybe module, and that is defined as the enum that is some t or none. Yo, so now rather than just doing that, mapping kind of like ad hoc kind of, oh yeah, let's just resolve the type. We now have we basically create types in these modules. I think that makes a lot of sense. Yeah. Okay, so I'm wondering, try to use built-ins.type. That type doesn't exist. Although, oh hell, it's like a colon instead of a dot. Oh, come on. Oh, come on. That is true. Yeah, that is very true. Hang on, where do we use colon? In some string interpolation here. Dot. Man. Yeah, okay, so this just resolves to $type. That's not in the map, that's true. Very true. Nice. Super nice. Yeah, I like that. Okay, so we do need some way of stopping, of just saying, I mean, yeah, we could just do, was that like an expand? Yeah, let's maybe do if the type starts with $, then don't expand or something like that. Does it feel hacky? Maybe, I don't know, but it works. So if variable dot string dot starts with $, then we just let's maybe do that like this. And then it's just the type. And I'll just close that. Well. Oh yes. Oh yes. Oh yeah, this is try to use call workspace call maybe with 0 arguments. But it needs 1. Also, this can fail. I didn't. Like, hang on, where is that error printed? Because it's not this to do. This to do is separate. We should fail at this error, wherever that is. So at some point we print something. Here. Right, map of all types. Yeah, okay, I guess that is fair. We'll just bubble that error up. Yeah. Okay. Very nice. I think I'm gonna stop it there for today. I'm thinking about maybe adjusting the imports and exports, because this is kind of weird, you know, that currently the let's see. Anyway, some modules export more than you think they would. For example, this int module, it needs the plus operator for strings, because when formatting a number, we kind of concatenate these digits into a giant string. But because it exports plus, it not only exports this plus function from int to int, but also the plus function from string to string. And that is ugly. You know, that the int module exports plus for string and string. In fact, there is no way currently to just, you know, if you have multiple plus functions in scope, to export one of them and not the other, which is really weird for situations like this. So I'm thinking about actually comma separating these like this. I think both imports and exports, not entirely sure. And yeah, basically have some sort of signature here. You know, we export the int type, but also the plus function taking int and int, and the minus function taking int and so on and so forth. Maybe with commas in between. Not entirely sure what that. Could do that. I could do that, yeah. Does that make sense? I think that does. Yeah, I think I'm gonna do that. Not today. I think, but sometime. And this right here would then look like this, importing the plus function from, adding strings for adding string. Yeah. It is a lot less concise than just writing the function name. But a bit more noisy, Well, I mean, I think at least if you have syntax highlighting, then these will be formatted differently. So if you have a long list of imports or exports, a lot of functions, then you won't kind of get bogged down by these. I think for operators it's kind of not a special case, but operators are especially difficult to read because they are so small compared to the ints. If you round up to multiple of, if you put an int here like this, seems reasonable, I think. Actually, you know what, I'm pretty certain I want to do this, so let's do something, something simple that I can still do right now without paying too much attention, which is adjusting the standard library. So checking if two bools are equal, and taking two bools, or taking two bools, x or taking two bools. I'm gonna put that on a new line, which means I'm going to put that entire thing on a new line, which means I'm not putting this on a new line. That implies taking bool of bool and format of bool. Dang, a lot of bool in here. Okay, and we import a string. I think that also makes a lot of sense. Yeah, bytes, that doesn't really exist. Neither does hash. I should at some point kind of either remove these or I should probably remove them, but no. Until I figure out hashing and bytes and so on, I'll just keep them there. Doesn't hurt. With ordering, we have string, and then exporting plus minus times divide mod and or XOR shift left shift right pow gate apps compare less greater round up to multiple of, round up to power of, square root log 2 equals font. Well, there's a lot of int here, but what are you going to do? At least the int module is quite big. Not in terms of objective size of the code, but it just exports a lot of these very simple functions. So I think modern not modern real world applications, they will export only a tiny subset of the actual functionality that's in there, because they hide that. That makes sense. The standard library is a bit of a special case, I hope. Yeah. Export list, oh, hang on, I think for generic types, we also want to have this export list of t. That is nice. It's actually, like, this is more descriptive and more, kind of easier to see what's going on there. Hang on. Do I want to do that? Or do I want to go all the way and be like, hey, you have to put things on the new line? That is like super verbose, though, so I don't think I like that. Although in this case, like, damn, that is clean. That is really clean. Yeah, I think I'm gonna do that. Yeah, just have everything on its own line. Oh man. Oh man. Yeah. I mean, you can't really read anything here. So I think it's fine if these are like this. And it leads to less diffs when you commit changes. That's also nice. And you have this sort of, I don't know, table of contents maybe, that you can quickly scan, and you can also like jump to these. I think that's, it can be a pretty useful tool, I believe. And yeah, the standard library main file will be quite long, but it exports it, like, it is quite big, the standard library, yeah, regarding just the sheer number of exports, so that's fine. Yeah, so let's start over with this one. Oh, do I want to allow this on a single line? I think so, actually. Yeah, why not? If you only import a single thing from a module, sure, feel free to do that. Yeah, it is a lot easier to scan, to be honest, so I'm quite happy with that. Hell yeah. Look at that. All these nice exports of ints. Int functions. Nice. I'm not entirely sure. Now I'd head towards going with the commas again, because this is ridiculous. It really is. And oftentimes, like, you don't really look at these, I think. Plus with syntax highlighting, it really kind of have to imagine how that looks like, but I think that's pretty readable already. So yeah, you know what? just do it like this, and that's fine. Oh yeah. Look at how nice and tidy that is. Cool. Hell yeah. We have the get function that, oh hang on, we import maybe t. Yeah, the get function that takes a list of t and an int. Get maybe function for list of t and int. The is empty function on list of t. Ooh, this is interesting. Several list functions actually. List of t and t, list of t and t and t. Len of list t, map of list t, and a lambda that takes a, let me say a, maps it to some b. A sum function on lists int, I believe. Yeah, okay. Very nice. We import never crash with string and string. We export maybe t and unwrap maybe t string. Oh, and unwrap maybe t. Cool. Very cool. And then in this one we import built-ins crash with string and export built-in crash string. Yeah, we import bool and string and we export nothing from nothing equals nothing and ignore any t. Export ordering and flip ordering. Yeah, import crash string and string, export result of O and E and unwrap of result of O and E. Amazing. Amazing. Export string and plus for concatenating strings. What's this? How's that even? That's not imported. That shouldn't work. Let's see. Look at some point it should fail. I'm curious how that's gonna look. Okay, so import built-ins type, yeah, type of some t, type info of type, export type info, field variant, type of t, type info of type. And this is also nice to see the signatures directly in here. I really like that. Especially for, you know, like the built-ins module, we don't even need to know the you can't look at the source code. And for packages, it is kind of inconvenient to have to look at the source code. Here we can just immediately see, oh yeah, you know, build a type info of type. That's cool. Okay. Yeah. So we also add a new import and export syntax. Oh, this PR, I don't use pull requests, but this this video will be quite long, I believe. Yeah, new import-export syntax, new type resolving, moving a lot of stuff from the yogurt to the egg, and I just got started with that. Like, I kind of underestimated how much effort that will be. But we do have correct, seemingly correct type resolving now. Before there were these subtle errors that are now no longer there. I think at some point I should also like document things a bit more extensively. I kind of started putting these section headers in here, but especially, like, I think this will be the compiler stage, toast to egg, that does the most amount of stuff. You know, the compiler stage where you really you get into the language semantics. You have comp time stuff in there, you have resolving functions in there, you have type checking in there. Like, this will be the compiler stage of the compiler, basically. And yeah, some part of that will still be in the conversion to yogurt, but the rest is just lowering stuff, compiling that to something like the backend, the compiler backend. Yeah, this is like the meat of this language. And so far, I think we're on a good track. Okay, yeah. All right. One thing I wanted to just check. Here we don't have a type, right? Yeah, okay. That's fine. Cool. What else? What else? Expanding types. Expand of some types. Oh yeah, what was the error here? Oh yeah, the import thing. I guess that's the challenge for tomorrow maybe. I don't know. Let's see. Having a new import syntax and working with that. See you then. Okay, parsing explicit imports and exports, including the types for functions and the generic parameters for types. Let's do that. I guess the first step would be in the toast, where we'll adjust how imports are represented. Yeah, here we have a toast import and export, and the import has a keyword that does, like, this is still there, and the import parts are also still there. Same with the exports. But the import parts, they have a module, that's true, and they have names. So this is where things differ. Rather than just having names in there, I think we'll actually need to kind of parse these things into something, into maybe signatures. So we have some sort of toast signature that has a name, which is just a string, and then args, I guess, or parameters or whatever. Oh, which will be a slice of something. I mean, we want to be able to pass something like this, you know, where we have a name, and then we also have, well, I guess types. Oh, and even for these, for these, this is just a type. I mean, for types specifically, it isn't valid to put anything else there except except a single type variable, but still that's a type. Okay, so this is a toast type. The arguments are actually just types. I like that. And then the imports, they are parts, yeah, and each parts has signatures, a slice of toast signatures, and same with the exports. Yeah, perfect. So we'll need to adjust bacon to toast and toast to egg. First bacon to toast. Yeah, here we try to create an export. Yeah, I think let's actually do like parse signature or something like that. On some line parser. And that just returns a result, maybe toast signature. And the way it does that is by passing an identifier. If there is no identifier, then we'll just say, well, there is no signature coming after here. So return no match. Like that. Yeah. If this worked, then we want to parse types. So basically parser dot parse type. Please tell me parse type is a thing. Parsing values, yeah, so here's parse type, where we try to parse structs and enums, and that is that, yeah, hang on, parse type that also exists on lines. Yeah, parse type expression is the thing we want. What is parse type atoms? Yeah, okay. Yeah, I don't know, parse type expression does seem like the right thing. If there is none coming, then we just break out of the loop. And we push that to the arguments. Like that. Oh yeah, this may return an error, in which case we want to bubble that up. In the end, we just return a toast signature with a name and args. Amazing. Conciseness, yeah. Ah yes, so this is a string and source. I think actually let's keep a string and source in there. I think that is useful information to have here. Like if a module doesn't export something and we try to import that, we can underline not just the import keyword where we have the source, but we can underline the specific thing that we're trying to import. That is pretty cool. Yeah, rather than names, we have signatures. And we do that by saying parse signature. And something very similar for the import, where we'll just say parse signature. And yeah, things should be like that. Let me open up a terminal because I haven't done that yet. So try to assign a list to type slice. Okay, 841, that's here. So what I want to do is say args is args converted to a slice. Oh yeah, because this can fail, that makes sense. It's for the import part, and this can also fail. Makes sense, yeah. Let's maybe put parse signature above the import and export because it is kind of more fundamental. Going on here, we have a signature which only has names and stuff. Oh yeah. That means we can even remove the curly braces. Clean. Very, very clean. So signatures.push. This doesn't work because it's a list of string. True, we want signatures to be a list of toast signatures. And same for the exports. Push list of toast signatures, string and something. Oh yeah, and here we also want to pass signatures. Actually, we want to also pass a comma. Like, there should be a comma or we're done. Same up here for the, or down here. No, here. And here as well for the exports. Try to pass the signature, then a comma. Consume doesn't work because this parser is not mutable. That is indeed true. Okay, pretty cool. So the signatures field is missing. weird. The signatures field is missing. 811 down here. True. Oh, why do we return early here? Parse import part and parse import. Oh, I see. Multi-line import is just handled up here. And all of this is for a single line import. I see. Yeah. I don't like that there is so much, you know, kind of duplication going on here. But, at least it's working. So we want to pass that, and then we also want to keep parser.consume column. Oops. Oh man. Same for exports, that's crazy. Okay, toast export takes a keyword, takes signatures. Okay, so we have the toast, fixed at least the static errors here, and then next step would be toast to modules. So we go through the signatures, and that means we have a signature. And if the signature name is uppercase, then that's a type. So in here we just put the name, which is the string at source. Oh man. Toast type definition. Yeah, and as the source, let's actually take the signature name source. That's cool. Okay, params is empty. No. Params should be... Oh yeah, and here should basically assert that these are just type variables. Something like that. And then in here the params, we can use anything. Oh, you know what, let's actually do that. That is a toast type, and that means it can be a variable. So we just want to take that variable, or if it's not a variable, then this is an error. And yeah, that basically gives us the name. And then we can do params.push name. And then down here we can say yeah, okay, so we build params and we build arguments, because why not? Yeah, seems fine, I think. And then in here we have params. We've fixed that. And then the arguments, we just use the arguments. Okay, yeah, I like that. I really do. Nice. Very, very, very nice. Mm-hmm. Oh. Yeah, this should be the arg source, underlining the argument directly. That's the idea. That doesn't exist on a type, only on a source. Okay, fair enough. Yeah, fair enough. Okay, so let's not do that and instead just have the name source. Yeah. Okay, so they are not correctly parsed, apparently. Here is the parse export thing. So yeah, the line is not just export, there was stuff coming afterwards, so there's a multi-line export. So what we do is we consume the export keyword, we check that there's white space, we build a list of signatures by looping over them. I feel like I've written this code like 4 times or something. You know what, let's maybe simplify. Pass signatures, plural. I like that. build a list of toast signatures. And what we do is we do signatures.push parser signature, or we'll just break, and then we do parser.consume a comma, please. And if there is none, then we also break. And then we'll just return that route. Here are the signatures. And of course this can fail, and then we build that up, and stuff like that. Yeah. Yeah, that's pretty cool. Okay. And let's also additionally do a parse signatures on a bacon, maybe. Not entirely sure whether we need that. Or rather on, I guess, a slice of bacons or something like that. Yeah, let's do that on a bacon. Sure. So what this does is it creates a parser. Well, it basically just does that. Creating a parser and then saying, you know, parser parse signatures plural. And then we need to be at the end. Boom, done. Actually pretty simple. Does that fit on a single line? Almost, but not quite. Yeah. And I'll also do the same thing for a slice of bacon. Basically for every bacon. Yeah, we kind of want to aggregate those signatures. So we do yeah, bacon.parse signatures. And we append all of them to the list. Oh, is there a like a append or something, or extend? I'm actually not sure. Something like that, maybe. Yeah, of course that can fail. And if there is none, then, well, oh, that can't actually happen. Because this one always returns parsed. Or it fails, but it doesn't return no match. Because even an empty line is bad. Nice. Yeah, okay, so for lists, is there a way of, let's maybe go into the standard library lists and see if there is some way of extending the list. Oh yeah, there's push all. I like that. I'm taking an iter or taking a slice. Beautiful. Okay, yeah, that's actually a better name, I think. Oh, indeed. Yeah, this is invalid. There need to be commas in between, and by the way, these are not correct because they don't specify the stuff, the types. Okay, yeah. So after we did that, we just say, well, we've passed the signatures. And then imports and exports, they become more trivial than they are currently. If there is a multi-line import, well, yeah, we pass import parts. And then we're done. Yeah. Oh, there's a bit more white space here. Okay, for a single line import though, we pass the import thing, then we pass the module, then we have the signatures, and here we can just say, well, pass signatures. And then we need to be at the end. Beautiful. Yeah, and this is already a slice, so no need for this one. Beautiful. Nope, not quite. But that's fair. Okay, yeah, then we have pass import part, which should also get easier. So what we do in here is we pass the module. And then we build signatures by checking if the parser is at the end. Yeah, in that case we just pass the children. Beautiful. Boom. Otherwise, our children need to be empty, and we pass the rest. This is kind of weird, kind of fishy. Hang on, let's maybe fix that. Let's say that, yeah, pass signature returns a result, maybe because it can return no match. But pass signatures returns a slice. So if there is no signature, it just returns an empty slice. That's totally fine, I think. Yeah, and then in here we just return okay. Like that. Same thing here. This can, oh yeah, this can go wrong if there is other stuff on the line, but if there isn't, then that just succeeds automatically. Yeah, same for slice of bacons. Yeah, that gets a lot simpler. Very nice. Okay, I like that. I really, really like that. So this is already a result. True, we should bubble that up if there's an error there. Yeah, this needs to be converted to a slice. True. Okay, yeah. Yeah, for a single line import, we just pass signatures. That may go wrong, so we do that. Clean. And then in here we have the we create a parser, we say parse a string. Here we try to parse signatures, but if that doesn't work, that's also fine. Let's say this entire if is kind of yields the signatures as a slice. Oh, hell yeah, I like that. So if we're at the end, then we just pass our children. Otherwise, those need to be empty, and then we do parser.parse signatures. Beautiful, ensure that we're at the end, and then evaluate to those signatures. Yeah. Then here we have a parse export, which will be pretty similar. We'll also use that. Multi-line export. Oh yeah, that will just do bacon with children, not parse signatures. Boom. Simple. Way simpler. And then otherwise we create a parser, we say let's consume the export keyword, and then there should be the signatures afterwards. And again we can just do parser parse signatures, which will return a slice. Clean. This is clean. Well, cleaner at least than before. Oh yeah, and we'll need to fix the standard library. Let's do that. And so we import several bool stuff. Yeah, that seems. Let's instead do it like this, I guess. That's a bit shorter. Boom. Yeah, I'm gonna fix the formatting later on. So we fix bools, we fix ints, we fix, we import everything that int exports. Yeah. Same with lists. Everything that the list module exports is what the core module imports, then maybe also exports stuff, and here we import that. The never module, it exports crash. String. Okay, the nothing module exports several stuff actually. Interesting. Ordering module. Exports ordering and flip ordering. Result exports some stuff, which we then import here. We take the string module, and finally the type module. Very nice. Okay, so let's now kind of wrap that on multiple lines as it makes sense. Should be more like this. This should all be indented one more. We have something different here. This goes on a new line. Yeah, nice. List is actually pretty long, so that gets broken up into multiple lines, like that. Yeah, I think the others are fine. Oh damn, no exporting. Well, that is fun. Yeah, I guess let's just put everything in here. And yeah, it may seem like weird or tedious or something, but first of all, this should be tool assisted, to be a bit less manual. But still, you might argue, it's kind of an anti-pattern if it requires tooling. But I think it's actually nice that once you have this, you have this kind of compact overview of what does this module actually export. I'd argue it is pretty interesting to see, and even a good thing to be aware of all the different functions that your module exports. Yeah, I'm gonna keep those within a single module on the same line. Just, Okay, yeah. Dang, I like that. Yeah, okay. Type imports should only have type variables as arguments. But the reported error location doesn't really make sense. Toast to egg. Interesting, with the signature name source. Apparently that's not working. That is strange. Just output something a bit more helpful and try to pinpoint it that way, but field isn't. And like type imports should only have type variables as arguments. Let's check those out. Here's field. Yeah, let's maybe print the argument. Okay, this does not seem correct. Int list maybe string, that seems weird. Oh, I see. Yeah, the core library is fixed, but not this one. Yeah, look at that. Nope. So this needs to be, first of all, multi-line, and then within this we just take field int list of t, maybe of t string type variant, that's for integers, minus for integers, list using a constructor, some sort of constructor. Oh no, we don't actually use that. Simple. Yeah, len of a list t, map of a list t, well, yeah, list a, using a function that maps a to b, sum of a list int and equals for ints. And that's what we want to import. Way more specific. I try to use workspace called type list, but that type doesn't exist. Called type. Does the type not import lists? It doesn't, so it can't use lists. Yeah, that makes sense. That makes total sense. Why wasn't that called before? I have no idea. Not built-ins. we do use built-ins, but we also use try to use workspace call type list with 0 argument, but it needs 1. Okay, that is that's both nice and bad. Like it is great that we now know that the list type takes 1 argument. That's pretty cool. But it should actually just take, like this takes 1, hang on, where's that? Try to use several places here. Okay, no, yeah, this one. So we have some sort of call. So far, so good. So we have the definition for that type. Let's also look at the type, maybe. Yeah. So we have the type, and we should also have a call type, call a lowercase type list. Yeah, right here. That is a workspace call list dot list of t. I mean, it needs 1 that is correct, and that is what we want to have figured out here. But we are providing 1, so what gives? Name is the call's name. Yeah. Not sure about that. Not sure at all. With 0 arguments. Why 0 arguments? That doesn't make any sense, I think. Oh, hang on. Alright, let's just debug this by, I guess, debug printing whenever we try to expand a type. Expanding is the type. I think that's a fair debug message. So let's see what happens. Okay, so we do stuff. Oh, this is a lot of expanding, okay. And where do we call expand from? Apart from, you know, expand itself. We do this. So let's maybe print an introductory expanding new top. I don't know. And this is like a top level defined type that we need to expand. So expanding a new type, this $type. And we're already done with that. Sorry about that. Didn't realize that I didn't have my mic. Okay. Yeah, so we're expanding a type. There's a built-in type, so nothing to do. Then we're expanding this right here. Interesting. I think this is the maybe type, basically. We want to expand that. So we expand the T and the empty struct. Done. Okay, expanding new type. This case, the core type. Oh yeah, and that gets expanded to workspace core type. So basically the type defined in the core module is expanded to the one from the type module. And that is expanded to built-in.type. Apparently that's the thing. Sure. And here we have the $type. That is because it's built-in type. Sure. Then expanding the next type. This time we are looking at maybe T from the core. Core package. So we're expanding T, we're expanding this, we're expanding the children. Okay. Then next type, the type info. That's an interesting one because it gets, first of all, it gets expanded into this. This is already wrong actually. Like this is an int with an empty struct, a string with an empty struct, a struct with a list, but it should have parameters. An enum with a list, but it should have parameters, and or a lambda or type. And yeah, sure, these empty structs they work, but this, like these ones don't. And that's weird. Now let me maybe print the toast. Maybe the toast is not even correctly parsed. Print the toast is simpler said than done because we have multiple toasts. But let's try to print every toast, I guess. So for every toast in toasts, we basically want to print the key, colon maybe, and then the value. Sorry, up front I'm gonna adjust the mic a bit. Okay. Okay, so printing toast is something we haven't done for a long time, which means the compiler stage changed so that the printing is no longer up to date. So, blah, blah, this is horrible. Oh, yeah, and imports are written in a really weird way. So we have the keyword and we have parts. That is true. So import, and then for every part in the import parse, we print a new line, 2 spaces, and then part, which means the part name, sorry, module, and then for every signature in the signatures, we print the signature. Simple. Yeah, and we do the same thing for exports. Well, not exactly the same, you know, because we only have signatures. We basically can't have only one part. So we just print export and then all the signatures that we export. Okay. Then we have this. We have write with some indentation. Yeah, writing a toast signature doesn't work yet. Let's fix that. I'm not entirely sure where to put that. Maybe here. I don't know. So we print the name and then the parameters, arguments. Yeah, toast types can be printed, so this should work. Okay, 189 members, we don't have members, we only have calls. That is pretty cool. You don't handle toast expression.enum. Let me guess, we have a, no, we don't have a variant because that's a call. Well, okay. So for enums, we just put the pipe there, then the name, and then the value. Seems simple enough. Maybe not. Because the value is a toast expression. And that doesn't work. Yeah. So instead, I think, yeah, we need this. We need indentation. Okay, so let's put a new line there, then print the indentation. And then do writer dot write enum dot value, like this. Okay, that seemed to work. Oh, not quite what I want, I guess. Oh, these all have indentation up front. I think we need that too. And this would be indentation plus 2, I believe. Yeah, then here we don't need indentation because this write takes care of that. Okay, yeah. Yeah, that looks fine. Okay, so let's look at the types. That's what I'm actually interested in. More specifically, that's cool by the way. Oh. Yeah. Writing signatures is a bit more difficult because, well, print a comma after and before everything, before every signature except the first. And we do exactly the same thing here. Okay, so oh damn. Oh, not quite. Yeah, it's initially true, and I hope that's also the case for the import. Yeah, okay. But apart from that, yeah, these look fine. This looks pretty cool actually. So what I'm interested in is the core type thing. That's what's not working right now. Dang, this is the core thing. Lots of imports, lots of exports. Yeah, core bool, horrible thing in here. We have the int module. We have the type module. Okay. So we import list of t. Perfect. We export several things. Fine. And this is type info. Type info is boom, this one right here. Oh, look at that. Sorry, no, only this line here. It's an enum that's either int or string or struct, and struct has a list of fields. Enum has a list of variants. Yeah, they are formatted horribly, but still. And then there's lambda type. And field is defined as this, variant is this. Like this looks perfectly reasonable. But for some reason, even though it says list of fields here, so these get parsed correctly. Despite that, the type info in here is basically, expanding new type, expanding this. It's trying to expand this type. We will just say, oh, this, that's a list of something, we don't know what. That's not correct. So when converting toast to egg, something goes wrong before expanding, basically. And I think we only do one thing. We prefix calls with module. So let's look in that. And let's say we have some sort of call. Yeah, so we have a name here. And we are, oh, this is expand. Yeah, this is the prefixed one. Let's look at that. We have a name. And then we build up these args. Oh, look at that. That is nasty. We call ourselves recursively, but we don't do anything with the result. Of course, we want to push that into this list of arguments. Bro. And yeah, let's maybe make sure that whenever we call ourselves recursively, we do something with that. Yeah, here we assign that to something here as well. Here we push that to arguments. We use that as the return type. Okay, perfect. And for these calls, let's also check that this does something with the arguments. Yeah, we zip them to create an environment of the expanded arguments and then do stuff with that. Okay, sure. That seems fine. Well, okay, so this is, again, an actual error. An actual, like, I'm not sure why these errors didn't exist before. Like, this code shouldn't have compiled back then, because they depend on string, and string is not used. Oh, I think it was lazily checked. Only if you use the type info type would you use fields, and only then you would use the string type, maybe. And only then it would figure out, oh, I don't know where that's coming from. Or even worse, it's somehow that got into scope. Now that we're doing that cleanly and upfront, you know, dealing with types, expanding them, we find these kind of errors. And actually, let's import the string type from the string module, which is the correct way to do that, the preferred way. Okay, so we've hit, yeah, this is a stack trace of a recursive call. Well, you saw that so nice before. Yeah. So we have a list of t. Call list of t. Oh yeah, so we expand the t, and then we expand the list of t, and then we expand that one, from the empty variant, and then that one from the more variant, again formatted horribly up there. That expands the t and a list of t, and so on and so forth. Well, yeah, that is true. I'm not entirely sure what to do about that, though. Yeah, okay, so this, just having an inner environment and having an anchor when expanding that is not enough. Because if we have some list of ints or list of fields or whatever, oh, hang on, can we actually see where where that initially came from? No, we can't. Try to be really fast, and not fast enough. Okay. Yeah, I could pipe that in the file and do stuff. So basically, if we have a list of fields, then the first thing we try to do is, let's say we have type info as our type. So the anchor is actually type info, and then we try to expand type info into the enum, into a list of fields. Okay, so we look at, this is a call, this is not the anchor, okay. So we get the name, it's a list, let's look at that list and do stuff and build up this inner environment where t maps to field, that's totally fine. Yeah. But we still need to be able to have recursions. We can't just rely on basically an outer anchor we have to yeah, I think in the yogurt, what we did is we had some sort of concept of parent calls or something. Parent, yeah, but not this one, but was it not here? Maybe not. Huh. Oh no, types got resolved in the egg already. Yeah, we got these parent calls. What would we do for, oh yeah, this one. This was the one that actually worked. Okay, yeah. So I think we need to do something very similar to this. Yep, have a depth and ongoing type calls, which are defined somewhere. Instead of anchor. Doesn't exist. But it had a name and arguments and depth. I think that's fine. Let's do that. Not sure about that one. Okay, we want to expand some type. Fair enough. You know, let's take this code down here as a baseline, I think. Yeah, to egg of some toast type. Would just do stuff. Actually, you know what? Damn. I think modeling recursive types using the, no, modeling recursive types using this approach, just storing how many levels above in the type we should continue. That works if the types are all specialized and concrete, monomorphized. It doesn't work if the types are still generic, I believe. For example, let's assume you have some type has an x, which is a we need some sort of recursive type. And let's say foo is something that's generic over T, and it contains a list of T. But now, if you create foo of okay, maybe it does work. Maybe it does work. Like, we never call a generic type. We never do something like this, t of int, and then you can specify list or map or whatever in here. That's not allowed. This is always a concrete, self-contained type. That may have internal recursion stuff going on, but it doesn't have recursion stuff in a general sense. So even for generic functions, generic types, it's totally fair to first resolve these to some, like to a concrete type, whatever that looks like, and then just store them in there. Yeah, okay. So let's do, well, let me keep that sketch in here. I'll remove that later on. Yeah, so expanding a type. using some environment. Okay, yeah. Basically, let's be like heavily inspired by this function down here. It has a type. We no longer have the definitions that are in scope and stuff, like, because names are all resolved. We have an environment and now hang on, this the weird function, right? Maybe? I don't know. So we have a parent, calls, and a depth. And for calls, somehow we do this. Yeah, and now I've copied that up here before and adjusted that. But now let's copy that again and adjust that again with more knowledge. So the first thing we do is lower the arguments. And I think that's actually a fair thing to do. And getting the name. And that's what we do here. That's totally fine. Then we check if we are recursively lowering a type, and I think that makes sense. Then this changed. This changed a lot. Because rather than having to go through all definitions and so on, the types are already in a map. Yeah, so we can already just do defs.get maybe of that type. And that is not, like, built-in is not a thing, a separate concept, it's just all uniform. So it's basically like we're trying to do this. We just, and even this is just for looking for the correct type actually. So we just have this. We have the called definition. Has to have the correct number of arguments, yeah. And then we build up an inner environment. Oh yeah, here we check the number of arguments, did that here. And I think it's fine to check that before, instead of down here. Okay, so then we build up this inner environment using the definitions parameters and the calls arguments. This is the interesting part. Yeah, this should use the arguments. Then we don't need to expand that anymore, because we've done that up top, up here. Amazing. so this has a type, an environment, parent calls depths. The depths are missing. The devs. And here the depth. Oh yeah, no, we already did that up there, so there's just the type. We don't really have calls after this. And we don't really have the egg, does it already use plum types? Hell yeah, it does. Okay, I think this already compiles that thing to a plum type. Well, that's something. Okay, so ongoing type call is something. Okay, here we do that. Sure. Oh man, this really is like the code below. I don't like that. But it makes sense. It just makes sense. I see that. Okay, let's copy that entire thing and then adjust that as needed. Okay, so don't actually put that down below, down here. We switch on the type. We do that too. For variables, we do something that looks quite the same. Yeah, I think this is actually saner. Okay. We have calls. Yeah, and I looked at that so many times. Lowering the arguments, yeah. Doing that. Looking for a type with a name, that got a lot simpler. And errors, okay, sure. Then structs, and there are still many to-dos in here, but that is fine, because we didn't do that up here as well. So this is just a map. Then in that map we put the compiled type. Using the environment, the defs. Same for enums, I believe. Yeah. And same for lambdas, I hope. Compiling the arguments and the plum types. Yeah, that's a bit cleaner. So let's do that similarly down here. And then we can just do that. Cool. Cool. Amazing. This is already amazing. So we check all types that you write in your code. That is cool. Compile all types. Do that, but not elegantly. environment, and the parent calls will just be this type right here. So compile toast type, map string to plum type. Should that? Yeah, that should be plum type. And map string to toast type def. Yeah. So this is just plum type. Okay. Map of all types is not a thing. That is true. Because it is called compile all types. Map of all types is just called compile all types. Beautiful. Well, this doesn't work. Okay. So what now? Now we have. Why doesn't this match? Oh yeah, because this needs to be a list, actually. Because the call needs to be able to like modify that and append items and remove items and stuff like that. Actually makes sense. Inconsistent return types. Yeah, true. So this is the signature to egg of something. These definitions have the same name, but arguments don't match. To egg. I'm basically going on an autopilot here. I'm not super deeply thinking about stuff. Okay, we have a to-do. That is nice. Okay, we are compiling a lot of types. Beautiful. And then what do we do? Then we print the expanded definitions. Let's do something similar to this. Okay, that is nice. That is really nice. So we're compiling types, and then we have this. Boom. Workspace core maybe, taking a T by the way, is just this plum type, an enum of none or some T. The type is just type, maybe again. Oh yeah, but not. There's the exported maybe type, core maybe, not core, maybe module, maybe. Crazy. Yeah, here we have the type info. That's cool. Like, this is totally expanded. You know, it's either a struct of this thing, and this is a list of fields, so either empty or more of this struct, which is the thing 2 levels up, chunk, another list item, and the item, and then a string or an enum. This is super nice. Yeah. Okay, so I think there were some cases where, first of all, there were some to-dos in here, sure, but I believe that this is not the correct behavior always. So when we encounter a type variable, we'll just look that up in the environment. But if it's not there, then we just assume, oh, this has to be a primitive type. That seems... I don't know. That seems fishy, you know. So rather than that, I think what we need to do is kind of a special case those built-in types. So if the type, toast type, yeah, if that is just the toast type for the built-in thing, which would be a call, maybe, I'm actually not sure, or variable, maybe variable. Hang on, up here we create these built-in types. using $, which is weird, but meh. Hang on, let's actually see. Where do we use that? Yeah, it's a toast type.variable of that. Oh, I see. So we can, in here we can actually check if variable string equals $type, then we just return, you know, type primitive type, something like that. Else, if it's $int, else an int. Else, if it is something, you know, string, that is. Yeah, we have a list of that type, yeah, of these. I should probably have a list for that. Seems about right. Type int, string, type, and never. Yeah, so in here we can just check if, like for every built-in type, otherwise, we don't, like, we never do this, you know. If env dot get maybe, if that's not in there, then that's actually a compiler error. Now I'm compiling type. Oh yeah. Okay, but now these are just the built-in types. They don't have a dollar in front of them. And more importantly, if you now write something like this, you're defining a type foo that depends on an A and it's a list of B. Now that should be an error. Before it wasn't. Yeah, look at that. Sweet error. try to use B, but that type doesn't exist. Beautiful. Beautiful. Okay, yeah, I like that. I really do. Let's maybe remove some of the debug stuff. So we have compiling, expanding new type. Oh yeah, another thing I want to improve is in here we build up this list of compiled types, like fully compiled types. And what we do is we, for every single type definition, we build up this environment of the arguments. We, have this thing. And actually, like, let's assume we have several type definitions. We have the definition of a list of T as an enum. What it does is it compiles that in here. So it figures out, okay, a list of T is actually an enum containing either empty or more or something. Let's go with maybe. Maybe is either some T or none. Okay, and we put that into this map. And then it's like, okay, so what's a maybe of int? Maybe that's another, like, we define foo as maybe of int. So what we would do is we would build another environment that is empty because foo doesn't take any arguments. And then in these definitions we would put foo is not maybe of int, but we would put an enum that is either some int or none. So like fully resolved. We made some, and then let's assume we have another type that depends on foo. Well, what do? We see, oh, there's a foo in there. During this compilation, let's look up the definition of foo. Oh, I see, foo is a maybe of int. Okay, so let's compile the int type. Let's figure out the definition of the maybe type, and let's insert int into that, and so on. So we redo a lot of work when composing types, because we compiled each of these types completely independently of each other, without reusing these, like partial work. When compiling this other type that contains the foo, even though we've just computed that foo is an enum with some int or none, we don't reuse that information. We just revisit all the definitions of recursive types, and so on. And that's a lot of unnecessary work, I think. So actually, let's simplify this. Let's say, rather than just running in isolation, this would actually get a kind of mutable thing to the compiled definitions. And it would also add types to this. So I think I'm going to split this into two functions. One is the compile raw, the actual compiler. Yeah, and this also takes an out thing, maybe, which is a map from string to type, a mutable map. And this down here also takes that map. Damn. Like, this signature is getting out of hand, but I think that's everything we need right here, so that's fine. Now let's put those on the same line. And all that this does is it calls actually compile, but only sometimes. So it calls it with a type at the end. The parent calls the depths, the definitions, and the out thing. I do wonder about recursive types. I don't know. You know what, I think I'm just gonna leave that as it was before and not worry about that, and do that when there are when I'm optimizing performance, you know. But I will note that I'll add it to do. I'm gonna put them in quotes to separate them from the text. Yeah, this is kind of weird because we don't compile these types in isolation. We don't just compile a list of t. And when we do this recursive work of this one. Hang on. Yeah, here. Here we don't just, let's say foo equals maybe int. And then at some other piece in the code we also have a maybe int. We can't reuse that because the first one will compile maybe with an inner environment of t equals int, and that is not like stored in here in the output thing. And this in here we only store a map from maybe to the type of that. Yeah, so we kind of don't deal with arguments here, which is admittedly weird. Like we should have maybe a tuple here of the plum type, but also the arguments that it expects. Yeah, again, we'll look into that. Okay. But cool, we have compilation of types. And I really like that we have this now down to something that works with modules, that is safe, that is sane, that gives you errors if type variables are not defined, or they are not in scope. We have this nice little section header that tells us what's going on. Yeah, so let's maybe remove some of the commented out code. Yeah. Resolving types, that's not something we need to do. Defs in scope is not something we need to do. We will maybe have some sort of this, funds in scope to get the functions that are in scope. I don't know. We'll look at that. And we have the exported funds. Not too sure about that, but sure. We have a prepare. This is like the main point of this module, and being able to compile the toast to an egg. Yeah, I think basically I'm gonna work through this module from top to bottom and kind of make that work. And I think now we've kind of finished with the one big section, basically the type level, compiling types. And like next, I think, oh hang on, here we can just return the compiled definitions. Yeah. As okay. And down here, this is what we'll look at next. This was the first part about types. Next is lowering functions. So see you in the next part, maybe.